But what we did back in chapter 2 was a very quick sort of, uh, you know, summary of this. And so we'll go into a little bit more detail because now we have more background so that we can actually do much more detail than what we did back when we looked at this first, like the first, second week of class. Okay, so chapter 10, correlation and regression. Section 10.1 is on correlation. And so first, let me talk about bivariate data. And so bivariate data. So bivariate data consists of, well, two random variables, X and Y. And we will denote bivariate data by an ordered pair, X comma Y, where again, X and Y are both random variables. And so a correlation between two variables is a relationship between two variables, so that a change in one variable results in a change in the other variable. A correlation is said to be positive or a direct correlation if an increase in one of the values of one of the variables results in an increase in the other variable. Similarly, a correlation is said to be positive if a decrease in one of the variables results in a decrease in the other variable. A correlation is said to be negative or an inverse correlation if an increase in one of the values of the variable causes or results in, I should never say causes, results in a decrease in the values of the other variable. Similarly, a decrease in one of the variables results in an increase in the other variable. So one way of visualizing this bivariate data is by way of a scatter plot or a scatter diagram, which is the graph of this ordered pair of bivariate data. And so let's say we have some bivariate data here. Let's say that I ask you your weight and your height. And so, here you're 5'10" and you weigh 170 pounds. Okay. Here you're 5'11" and you weigh 190 pounds. So each of these points here represents a value for this bivariate data. So we're asking you two things, your weight and your height. And we plot, all your weights and heights. So what you notice here in this particular case, there's a positive correlation that it seems that this was weight and height, right? That the more you weigh, the taller you are. So it seems that there's some sort of relationship that taller people, weigh more, or people who weigh more are taller, and people who are shorter seems to tend to weigh less. Okay, so there seems to be some, in this case, positive correlation. Now, or in this case, we seem to have some negative correlation. Okay. Now, in this case, we are this R here in the graph is called, well, Pearson's product moment linear correlation coefficient. It is always between -1 and +1. It measures, well, how close is your correlation to a linear, how close is your data to a linear correlation? So how close are you to a line? some particular line. Let's say, in this case, I'm just doing it by eye. I'd say this particular line. How close is all this data, here, to this line? First, if there's a positive correlation, then this number R will be positive. Whereas if there's a negative correlation, this number will be, this, R here will be negative. If this data is close to this line, then this number here will be closer and closer to 1. Well, disregarding the sign, it'll be closer and closer to 1. So notice that, that's a pretty good correlation, but not as good as, 0.851 is a good correlation as compared to 0.965, which is much better. And so the closer these numbers become to 1, the closer this data is to this line. So that's what R is. And so if, well, I don't know, say this one or whatever. In this case, there doesn't seem to be any line that's close to. And so in this case, we have no correlation. There doesn't seem to be, as you increase X, it doesn't necessarily increase Y. So it's all spread out. So in this case, I'd say there's really no correlation. Next, this R here only measures how close you are to a linear correlation. So this has a correlation. So this is actually, very close to some, in this case, nonlinear relationship. Now, it's neither positive nor negative correlation. This is in this case, looks quadratic. So this looks like a parabola. But it has virtually no linear correlation. So this has no linear correlation. And so this is virtually 0. And so, here there's a little bit of linear relationship, but almost none. Obviously it's not linear. It's parabolic. So in order for us to talk about a linear correlation, we must have that this ordered pair must come from from a simple random sample of quantitative data. So each of these are quantitative. We must have that a visual examination of the scatter plot must confirm that the points are an approximate straight line pattern. Because again, this has no linear relationship, but you might be misled to think it has a little bit of linear correlation because this is some number, but notice it's not linear. So you have to look, does it look like a line? This doesn't look like a line. These look like more or less they're close to a line. There seems to be some sort of linear relationship in the data. Outliers. So outliers can greatly affect all the calculations we're going to do. And so outliers must be removed if they're known to be errors. So if you look at an outlier and you go, well, that can't possibly be, a person can't have a negative age. And so, or maybe a weight. They can't have a negative weight. Okay, so that must be an error. They can't have a negative height. So some of these are known to be errors. Just remove them. For the other ones you can't remove, then you have to do two calculations and two sort of analyses. One where you consider the outliers, the others where you remove the outliers. So you do two separate sort of analyses. You graph everything, you look at it both with and without your outliers, and then you let the reader decide for themselves, well, what they should discern from this. So it could be that you have like this, looks like a nice line, but then you have an outlier here, and then when you do the now it looks like this line rather than this line because of this outlier. So it could be that one outlier could greatly affect the value of R, in this case, the regression line, the line that all this data is close to, could be greatly affected by having, some, the outliers here that move this line. Let me give you some of the properties of, again, I'll just call this a linear correlation coefficient. It is properly called Pearson, for the person's names, product moment linear, and this is in sample, and this is actually the sample linear correlation coefficient. I'll just say, actually, usually I won't even say linear. I'll just say the correlation coefficient. So usually, or just R, and to sort of abbreviate what I'm saying there. Okay, so R is always between -1 and +1. So negative purely indicates it has a negative correlation. Positive merely indicates that it is a positive correlation. It has nothing to do with, the slope. It's just once the slope becomes negative, then it's a negative correlation. The closer R is to 1 in absolute value, the closer the data is to a straight line. If all the data is on a straight line, then R is equal to either +1 if it's positive, or -1, well, whatever, or -1 if it has a negative correlation. If all the values of either variable are converted to a different scale, the value of R does not change. And so, R of AX plus B, comma, CY plus D, it doesn't matter the B's and D's. This is the same as R of AX, comma, CY. Next, well, it virtually doesn't matter what the A and C are. The only thing is that maybe one, I multiply one of these is positive, the other is negative, in which case then you'll switch around, the correlation will change sign, but it won't change magnitude. So this number here just says that if A and C have differing signs, then this number here will change sign. If if A and C have the same sign, then R will remain the same. So maybe I should say that this is equal to plus or minus R of XY. So, and this tells you what the actual plus or minus are. So it's exactly the same for almost all cases, except when, you strangely have that, these signs are different. And so if these signs are different, then all it does is change the sign of the correlation coefficient. Next, if AX plus BY plus C equals 0, meaning that if you're on a line, if every point here lies on a particular line, then R is equal to, again, I should probably say it this way, is equal to plus or minus 1. It's equal to positive 1 if the signs are different. It's equal to negative 1 if the signs A and B are the same. The signs of A and B are the same. The value of R is not affected by the choice of X and Y. It doesn't matter if, you could interchange the dependent, independent variable. So interchanging all X and Y values does not change the value of R. So R of X comma Y is the same as R of Y comma X. Let me just check something for 1 second. Any questions? Also, I want to check I'm recording just to satisfy my paranoia. Oh, there you go. Oh, is there any way to zoom up? Meaning?
Oh, never mind. I couldn't see it the board before, but I figured it out. It's good now.
Oh,
Thank
okay.
You.
Okay then. Okay. Next, R here measures the strength of the linear relationship, more or less. R is very sensitive outliers, and so these can dramatically affect the value of R. So that's why we remove outliers that are errors, and that's why we both include and don't include the outliers, because the value of R can be greatly affected by these outliers. If X and Y are independent, then the correlation is 0. But the converse is not true. And we've seen that before. We've seen that, if they all lie, let's say on a parabola, the correlation could be 0, but they're dependent. They all are related in a quadratically to each other. So there could be some relationship between X and Y, yet the regression could be 0. But if there is no relationship between the variables, then the correlation coefficient is 0. So this will now sort of tell you better what I mean by R measures the strength of the linear relationship. So the value of R squared is the proportion of variation in Y that is explained by the linear relationship between X and Y. And most importantly, correlation does not imply causation. The mean for the sampling distribution of all sample correlations is the population correlation. So R here is the sample linear correlation. Rho here is the corresponding population correlation coefficient. The standard deviation for the sampling distribution of all possible sample correlation coefficients is the square root of 1 minus R squared over nu, where nu is n minus 2, and R will the sampling distribution of my sample linear correlation coefficients will follow a t distribution with, again, degrees of freedom equaling n minus 2. And you can think, so before, degrees of freedom were always equal to n minus 1. from now on, things are going to change. So up until now, degrees of freedom were always n-1, but that changes now. In this case, well, think you've got to take away one for the x and another one for the y. So n-2. So this gives us a way to do hypothesis testing for correlation coefficients. The confidence interval for rho is r plus or minus e, where e is equal to t times 1 minus r squared over the square root of n. Where, again, to figure out the critical t value, I use the fact that my degrees of freedom are equal to n-2. A better estimate for my confidence interval for rho is e to the power 2w minus 1 divided by e to the 2w minus plus 1, comma, e to the 2w plus minus 1 over e to the 2w plus 1, where e plus or minus is 1/2 ln of 1 plus r over 1 minus r, plus or minus the z critical value divided by the square root of n-3. So the linear correlation coefficient. So the sample linear correlation coefficient, R, better called Pearson's product moment sample linear, actually I should have said here sample. Linear correlation coefficient measures the strength of the linear relationship between paired x and y values in the sample. Again, we assume that the sample pair data x, y are from a simple random sample, and they're taken from a bivariate normal distribution. R here denotes the sample correlation coefficient, whereas rho here denotes the population correlation coefficient. So let's recall from section 5.1 that we defined the covariance of x and y as the expected value of x and y minus the expected value of x times the expected value of y. We also showed that this is the expected value of the product x minus expected value of x quantity times the quantity y minus expected value of y. Sometimes we denote the covariance as S sub xy. So I'll give you several formulas to determine the correlation coefficient. So R is equal to S sub xy over S of x times S of y, the regular standard deviations for x and the standard deviation for y. It's equal to S sub x comma y, the covariance of x and y, divided by the square root of the product of their variances, the square root of s squared sub x and s squared sub y. It's equal to the sum of x minus the mean times y minus the mean over my degrees of freedom, n-2, s of x times s of y. It is equal to the sum of x minus the mean times y minus the mean over the square root of the sum of x minus the mean squared times the sum of y minus the mean squared. It is And this is the simplifying computational formula, which actually, if you look here, looks very similar to the simplifying computational formula that we had for the standard deviation or variance. It's equal to, and now you just sort of do the same thing for x's and y's. And so it's equal to n sum xy minus sum x times sum y over the square root n sum x squared minus sum x quantity squared times the square root of n sum y squared minus the sum of y quantity squared. Let's do an example. For the following data, and we'll just be using this, I guess. For the following data, obtain the value of the correlation coefficient R. N is equal to 10. Okay. And so in here, I guess we're going to, well, it's the same thing here. So n here is equal to 10. Sum of x, y, 7,900. Sum of x, 250. Sum of y, 300. Divided by the square root of n, 10. Times the sum of x squared, 6,500. Minus the sum of x, 250 squared. Times the square root of n, 10. Times the sum of y squared, 10,000. Minus the sum of y, 300 squared. And you plug that into your calculator and you get 0.8. Okay, now let's do the following example. Suppose I have the following data. When x is 1, y is 2. When x is 3, y is 7. When x is 5, y is 5. Let's determine the correlation coefficient, R. And so I'm going to be using this simplifying computational formula. So I have here x and y. I'm going to multiply first and second column to get the third column. So all this looks very familiar, to what we've done in chapters 3 and above. And so 1 times 2, 2, 3 times 7, 21, 5 times 12, 60. Next, multiply the first, square the first column. So 1 squared, 3 squared, 9, 5 squared, 25. Square the second column. 2 squared, 4, 7 squared, 49, 12 squared, 144, and add. And so 9, 21, 83, 35, 197. And then you plug into your calculator. And so, for n, you got to add. You got to count. 1, 2, 3. So n is 3. Sum of xy, 83. Minus sum of x, 9. Sum of y, 21. Over the square root of n, 3. Sum of x squared, 35. Minus sum of x, 9 squared. Times the square root of n, 3. Sum of y squared, 197. Minus sum of y, 21 squared. And you plug that into your calculator and you get 1. Okay, so let me do that. Oh, okay. It's going to be that way. Okay, so let me stop sharing. Okay, so let me do the TI-84. Let me put in my data. And so 135. And let's store that in L1. And let's put in the Y's, 2712. And let's store that in L2. Okay, so in L3, I'll do L1, L2. I'll store that in L3. Then L1 squared, I'll store that in L4. And L2 squared, I'll store that in L5. So now, if I look, voila. So here is what I had in my table. So here's my table here. So here's all my numbers in my table, other than the sum, but we'll be able to do that in a second. So here's all the, the numbers in the middle of the table. So now let me quit that, go to stat, calc, and 2var stats. So this is the first time we've seen this 2var stats. Let's do that. L1, L2, actually, that's what I want. I want L1. I have them listed in L1 and L2. And so I have here the sum of X, 9. The sum of Y, 21. The sum of XY, got to go down, 83. The sum of X squared, darn, got to go back up, 35. The sum of Y squared, 197. Okay, there it is. Good. So those are all the numbers I plug in. And now, actually, let me okay, so I had to do something in the background. So if I then go to stat, calc, let's do that, linear regression. Yes, everything's, so L1, L2. Well, doesn't tell us anything, but notice the following, and you only have to do this once in your life, and this is the weirdest thing ever. You go down to catalog. So you do second, catalog, and you go to find what's called diagnostics on. So it says diagnostic on. You got to turn the diagnostics on. Okay. And then you enter. And then when you go back, now I'll click on stat, go to calc, and let's go to the 8th one down, linear regression. We'll do the same thing, L1. L1 is the X list, L2 is a Y list. Nothing else is there. Now when I do the calculation, now I see this. Now I see R. So they did R for me. In this case, they went through and did the whole calculation, and they said R is equal to 1. So now everything that I have on my iPad is now just read off from the TI-84. Any questions about the TI-84? Okay, let's do this. So again, all this data, so I input this data, and then, I let the computer do everything else. It gave me all this stuff. I just put this, read off all these and put that in here. Other than I had to count 1, 2, 3. That I have to count. And then, actually, get rid of that. Then I found this by, again, just doing it on the calculator. Calculated it for me. So I'm really just reading off basically what the calculator is telling me. Okay, so let's do this again. So I'm going to do virtually the same thing. I'm going to, so here I have when x is 3, y is 14, dot, 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 dot. When x is 13, y is 20. I'm going to put into L1 my x's, into L2 my y's, and then do L1 times L2, that'll give me L3. L1 squared is, I'll store that in L4, L2 squared, store that in L5, and label your, read, basically, I'll just label this x, y, x squared, y squared. And then I'll go to the TI-84, go to stat and look at edit, and I'll just read off all these numbers. Then I go to var stats, L1, L2, and read off all these numbers. Then I'll be able to plug in to this formula, other than the fact that I've got to count 1, 2, 3, 4, 5, 6, other than the fact that I have to count n, which is 6. Okay, so let's do this. So now let's do this here. Now, any questions so far on what I'm going to do? Okay. So let me, oops, I have to stop the sharing. Don't know why I have to do that, but okay, so I've got to stop the sharing here. Okay, so let me go to my one var stats, to my TI-84. That'd be 2 var stats, actually. Okay, so let me input 3, 8, 10, 2, 6, 13. Actually, I should also show that. And let's store that in L1. Next, 14, 22, 24, 15, 16, 20. And let's store that in L2. Okay, so let's do L1, L2, store that in L3. L1 squared. Let's store that in L4. L2 squared. Let's store that in L5. Okay. So now go to stat, edit, and now I can read off all this stuff here, and that will give me, and then, well, put it into, my paper or whatever when I'm doing this on an exam. And it looks like I've done a whole bunch of calculations, and I really haven't. I'm just reading off all the stuff that the computer's done for me. Okay, next, let's quit. And let's go to stat, calc menu, 2 var stats. L1, L2, that's all I want. And so read off the sum of x 42. The sum of y, 111. The sum of xy, I guess you have to go down. 844. The sum of x squared, 382. The sum of y squared, 2137. Put all that into my formula, the simplifying computational formula. And now let's go to stat, calc, and I'll go to the 8th one down. And all that is still the same. X list is L1, Y list is L2. And there's R. 0.7816102191. So again, it looked like I did a whole bunch of work here, but I really just, input the data and basically the computer do everything else. Okay, any questions about this? Okay. So, good. Okay, so, actually, I should have done this. Let me go back. Well, maybe maybe for the next one, I'll show you how to graph it. Okay, so I'll show you how to graph it with the next one. I should have shown you what the data looked like. But yeah, actually, let me go back for a second. Let me go back. Let me just show you what all the data looked like. Okay, so let me go back to my TI-84. Okay. And so if I look at this, let me quit out here. Let me get rid of all this stuff. Okay. Everything's off. Okay, so I want that first one. Want to turn it on. And I guess I want scatter plot. Blue looks good to me. Let's just see what does my window look like. These numbers go from 1 to 15, let's say. And Y goes from 10 to 25, let's say. 12 to 25. Okay, so now, there. This is what my data looks like. So there's the data. And let me actually do something. Let's go to Y1. VARs, statistics. My regression equation. Okay, so now actually let me. So so this is the line that it looks like. So this is, here are all the data points, all my data. And it sort of looks like it's somewhat close to this line. It's not great. That's why, the correlation was 78.78. So it's, close, but not like right on top of the line. Okay, so let me go back to my other computer, to my iPad. Okay. Okay, so the paired shoe height data from 5 males are listed below. Use a computer or calculator to find the values of the correlation coefficient R. So here are the shoe print from 29.7 to 27.6. Here's the height, 175.3 to 172.7. So let me plot my data. And that's what I'll do on my calculator. And then let's try to, do the following. So note, if I'm trying to see, is there a correlation? Then I would say, well, let's see. The null hypothesis always has to have an equal sign. So there's no correlation. Null hypothesis, these are not related at all. The alternative hypothesis, there is some sort of correlation. Rho is not equal to 0. And let's say alpha equals 0.05. And so let's do this. So let's actually find what R is and, well, what the p-value is. And let's do that. And let's figure out what R is. And let's actually look at its regression line just to look at it. Okay, so let me go on to my calculator. Oops, I have to stop sharing for a second. Okay. Okay, so let's put in my data. 29.7, 29.7, 31.4, 31.8, 27.6. And let's store that in L1. Next, 175.3, 177.8, 185.4, 175.3, 172.7. And let's store that in L2. Okay, I could make up the table again, but maybe I'll just figure out what R is. Stat. Let's go to okay, so L1, L2, and it is not equal to 0. There it is. Okay, so I have here the p-value, p here, is 0.2936, well, 86. Maybe I should put it all down. 0.29, 0.2936, 86, 3226. Okay. find what they're A and B, and here's R. So here's R. R is 0.5916 0.59126 90853. Okay. And let's see. Let me put down my data. Let's get rid of that and go to VARs, statistics, the equation, EQ, and the regression equation. Okay. So, and then let me go to the window. These numbers are from, let's go from 25 to 35. And from 170 to 190. So it'll look like what's in the, and then let's graph it. So, so it'll look like when in my lecture notes. So here is all the data. And here's the regression line. Okay. And we found that the the correlation coefficient was 0.29, 36, etc. Okay, so let's go back. Oops, not new share. Let me go back. Any questions so far on what we've done on the calculator? Okay. So I have here that we found. So here's what our data looked like. I actually drew a little line here, the regression line. And if I were testing if they're correlation or not, I found a p-value of 0.29, which is 29%. It's much bigger than 5%. So my p-value was greater than my alpha. Since p is greater than alpha, then I am not in the rejection region. So I do not reject the null hypothesis. So I'm not rejecting this, which means that there's no correlation. Oh, so this guy's, so the 0.59, that is too small. And so, no, there is no correlation here. There's insufficient statistical evidence to support the fact that there is a correlation between shoe print height, the shoe print, and height. Okay. So, and we could also have done this by looking at, here. So I could have also done this by looking at the following, looking at this table. So in this case, well, let's see, how many? 1, 2, 3, 4, 5. So the sample size is 5. And we have alpha is 0.05. So the critical value is at 0.878. So the critical value here is at 0.878. And so my rejection region here is just, here are the critical values at plus or minus 0.878. I found, so here's my hypothesis test. Null hypothesis, rho 0, there's no correlation. Alternative hypothesis, rho is not equal to 0. There is some sort of linear correlation that alpha equal 0.05. My test statistic, R, was 0.5912690853. My critical values were found to be at plus or minus 0.878, which means that my test statistic is not in the rejection region. So therefore, we do not reject the null hypothesis. Since I did not reject the null hypothesis, then there is no linear correlation between shoe print and height. Any questions about that? Okay. The value of R squared is the proportion. So this is a variation in Y that is explained by the linear relationship between X and Y. So we found that R is, here it is, 0.591. So R squared is 0.349. So we can conclude that 34.9% of the variation in height can be explained by the linear relationship between the lengths of shoe prints and their heights. The other 65.1% cannot be explained by this relationship. And so somehow there's 65% of the variation in your height that's not explained by how big your feet are. So again, causation does not imply causality. So it is wrong to conclude that correlation implies causality. Averaging suppresses individual variation. It may inflate the correlation coefficient. There may be some relationship between X and Y, even when there's no linear correlation. And again, correlation. Section 10.2, regression. So the best fitting line curve is called the regression line, and this equation is called the regression equation. And so recall that, well, the typical equation of a line is y equal mx plus b. In statistics, we give it, different sort of letters here. And so instead we write it as y, well, y hat, equals b0 plus b1x, where b0 is the y-intercept and b1 is the slope of your line. And so let me go over some of the notation. The equation of a regression line for my population is y hat equals beta 0, the y-intercept, plus beta 1, the slope, x. Whereas for a statistic, the equation of your regression line is y hat equals b0, the y-intercept, plus b1, the slope of the regression equation, x. And so, just like before, for samples, for statistics, it's letters, lowercase letters, and for parameters, it is Greek letters. The corresponding Greek letter. So, corresponding Greek letter of B is beta. So, we'll assume that X and Y are random variables having a normal distribution with the same variance and mean lying on, and the same variance, and that the mean is lying on the regression line. And so B1 is, the slope is, well, the simplifying computational formula, again, looks very similar to what we had for the equation for your variance in chapter 3, n sum xy, and also for the correlation coefficient. N sum of xy minus sum of x times sum of y over n times the sum of x squared minus the sum of x quantity squared. It is s of xy over s of xx. It's the covariance of x and y over the variance of x. R times the square root of s of xx times s of yy over s of xx. It is r times the square root of the variance of sample variance of y over the sample variance of x. It is r times the standard deviation of y over the standard deviation of x. So I calculate, the slope here using usually this formula, but there's other relationships that can be used, especially if you know something else, then we can, use those other formulas. The y-intercept, b sub 0 is, again, the simplifying computational formula, the sum of y times the sum of x squared minus the sum of x times the sum of xy over n times the sum of x squared minus the sum of x quantity squared. But actually, I never really use this formula because this is easier. It is, well, you just, take this and solve for beta 0. So you just bring this on the other side. And so B0 is the mean of y minus B1 times the mean of y, that mean of x. And so, that's a much easier form. So once you've figured out B1, to figure out the y-intercept is much easier. Just do the mean of y minus the slope B1 times the mean of x. So again, remember, an outlier is a point that lies far away from the other data points. An influential point is a point that strongly affects the graph of the regression line. A residual. For a paired data, x, y, the residual E, the error, is the difference y minus the actual y value minus the approximated y value using your regression equation. And so E here, the residual, is just y minus y hat. And so notice, just like when we're looking at in chapter 3, when we're looking at the sum of all the deviations from the mean, well, the sum of all these deviations from the predicted value of y is also 0. So how do we sort of figure out this predicted value of y? Well, again, we do the same thing that we did from before, is we try to minimize the square of these differences, the square of the errors, the square of the residuals. So the least squared property is the following. A straight line satisfies the least square property if the sum of the squares of the residuals is the smallest sum possible. And so the least square property minimizes the sum of the squares of the residuals, the sum of the squares of these errors. So if I look here at what we had from before, we would like to use the explanatory variable x. This is x. to predict the response variable y. So maybe I should put an x here and a y here. Oops. Okay. Okay, so let's try to somehow, if you have a particular shoe print, what is your height? So I look at your how big your feet are. I want to figure out how tall you are. Okay, so the data is assumed to be a simple random sample. And we looked at the scatter plot and we noticed it was roughly a straight line pattern. There's quite a lot of variation, but it was more or less straight line. And there were no outliers. And we did this calculation here. And we found, well, so here's the, here are all my points. And here was the regression line. So let's actually, so rather than, we can actually look here and find the sum of the residuals, but let's actually do one of them by hand. Okay, so we found that the regression line was, well, let's see, A. Here it is, 125.4073302 plus 1.72745x, or 5239x. And so we have, well, let's look at one particular data point, this guy. So let's look at this guy here. So I know this is y. Question is, well, what is this guy? So then I can figure out from here my residual, which is just the, this y minus y bar. Okay, so here's my residual. So I plug in the 31.4 and I get 179.65-ish. I subtract that from the actual y value, so 185.4, to get 5.75. I then can plot x and the residual. And so this is called a residual plot. So this is, quote unquote, the errors. So I can look at my residual, so I did it for one value. Probably for 31.4. It was this guy. I think I did for this guy here. So I think this is the point here. So I found the residual for this guy. How far is, so this is my residual here. This distance here is 5.75. Okay. No, actually, it's this point. Well, whatever. It's this point here. I'm sorry. It's this point here. I labeled it, matter of fact. We found that this distance here, maybe I should. Is 5.75. So that distance there is 5.75. And I can do it for all of these points. And do a little plot here. Okay, so we should use the regression equation for predictions only if the graph of the regression line in the scatter plot confirms that the regression line fits the points reasonably well. Not too horribly bad, not great. Use the regression equation for predictions only if the linear correlation coefficient R indicates that there's a linear correlation between the two variables, which, whatever. Oh, which was in the last section. which was in the last section. Sorry. In the last section, we did that. And we found that there was no correlation. We actually found, so for this data, we actually found that there's no correlation. Use the regression equation for predictions only if the data does not go beyond the scope of the data available. So meaning, here's all the data, here's the line. It doesn't really say anything about stuff way out here because I'm too far away from the data. So, if I try to figure out, if you're 85 or something, then who knows what, you can't extend this line out forever. Okay. So predicting too far beyond the scope of the available data is called extrapolation. And we're doing interpolation, not extrapolation. So this could result in bad predictions. If the regression equation does not appear to be useful for making predictions, notice this was not satisfied. So in this particular case, the best predictive value of y is the sample mean of y. So, we looked at this, is the regression equation a good model? Does the scatter plot show that the data fits the line? That the line fits the data? Okay. Yeah. Does R indicate that there's a linear correlation? In our case, no. Is the prediction not much beyond the scope of the available data? Well, yeah, it's not. And so it's still a no because of this guy here. Then the regression equation is not a good model. So regardless of the value of x, the best predictive value of y is the mean of y. If instead it satisfied all of these conditions, then yes, the regression equation is a good model. Then you would substitute the given value of x into the regression equation, the 179.65, and that would give us a good predicted value of y. In our case, the answer is no. So, here it is. So let me explain that again. Use the 5 pairs of shoe print lengths and heights to predict the height of a person with a shoe print length of 29 centimeters. And so the regression line does not fit the points well. The correlation R equal 0.591 suggests there's not a linear correlation. Remember, I think it's 0.8 something. And so the critical values was like 0.84 or something like that. I don't remember exactly. But this was within that was not in the rejection region. So I didn't reject the null hypothesis that there was no correlation. And so there's no correlation. Therefore, this suggests that there was not a linear correlation. Also, the p-value was really small. It was really large. So p-value is really large. It was 0.294. So again, we rejected null hypothesis. So the best predicted value of the height is the mean of the heights. So you just add up all the heights and divide by how many there are. So it's 177.3 was the predicted height, which is a better predictive value of y than the value you would get from the from the regression line. Because it's a different point. Because that's a different point. I'm sorry, that's 29. So this is not the best predictive value. The best predictive value is your mean. Now, if you used instead the 40 pairs of shoe print lengths in data set 2 to predict the height of a person with shoe print length 29, now the regression line So here's all this data. So they're 40 rather than 5 numbers, they're 40. And it fits it better because there's, seeing that there's more numbers, well, this actually isn't too bad. The correlation is now 0.813. Which barely suggests. And so that's but now you look at 0.813, the critical numbers are actually going to be different. The critical values are going to be different. And so it's actually in the rejection region. So the p-value is like 0.000. So it's in the rejection region. So we reject the null hypothesis that there is no correlation coefficient. And so this suggests that there is a correlation coefficient. And so we have that y is equal to, in this case, 80.9 plus 3.22x. Plug in your 29, and you get 74.3. So in this case, you would use the regression line. And so you say that, well, a person with shoe print length 29 centimeters predicted to be 174.3 centimeters tall. Okay. So the marginal change. So in working with two variables related by regression equation, the marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. The slope B1 in a regression equation represents the marginal change in y that occurs when x changes by 1 unit. So for the 40 pairs of shoe print lengths and heights, the regression equation was y hat equals 80.9 plus 3.22x. The slope 3.22 tells us that if we increase your shoe print length by 1 centimeter, the predicted height of a person increases by 3.22 centimeters. So for every increase in your shoe print, your shoe, the length of your shoe, or the length of your foot, let's say, for any, for every 1 centimeter increase in the length of your foot, you expect to be like 3 centimeters taller. Shoe print length is, obviously will correlate to your length of your foot. So in this case, I'm sort of equating the two, but, so increase in the shoe print length by 1 centimeter increases the height of a person by 3.22 centimeters. So again, an outlier lies far away from the other data points. An influential point strongly affects the graph or regression line. So suppose we have the following. For 40 pairs of shoe print and heights, observe if we include one additional point. So here, here is the plot of the 40 pairs of data. So here are the 40 pairs of data. Let's add one other point. X is 35 centimeters and Y is 25 centimeters. And now, what does the regression line look like? It now looks almost flat. So adding this one additional point here has changed it from looking like this to looking like this. So it greatly affected what the line looked like. It brought it down quite a bit because of this one point. Of course, this one point, so this is called an influential point because it dramatically affects the regression line. In addition, this is also an outlier because it's far away from all the other data. So it's an outlier because it's far away, and it's an influential point because it has influenced a dramatic change in the regression equation. Of course, this is a really strange person. His foot, he basically looks like this. So here is this person. He's got big feet. So he's got gigantic feet. His feet are 10 centimeters bigger than his height. So he's basically just two big feet. And that's it. So he's got these he's only 25 centimeters tall, but he's 35 centimeter shoe print length. So his shoes are much bigger than his height. So it's a very strange looking person. Obviously not a real person. Then a real person's not going to be have these floppers for feet or whatever. Okay. Okay, so again, the residual. So the residual is the difference between the observed sample value y and the predicted value y. And so let's suppose we have here some data. Let's say one negative. Oh no, that's a residual plot. Don't look at the residual plot yet. Okay, so I have here the point 1, 9, 2, 13. No. So 1, 4. Sorry, here's the data. Stupid. The data is 1, 4, 2, 24, 4, 8, and 5, 32. So these are the data points. Here are your data points here. Maybe I should have done them in blue or something. So 224. One, 4. Eight. And 532. Okay, good. Okay, so here are my points here. Let me show the following. So let's look at the point 224. And my regression equation is y equals, say that. Here it is right here. My regression equation is y equals 5 plus 4x. So let's see what the predicted value is when when x is equal to 2. So I get y equals, 5 plus 8 is 13. And so 224. So my predicted value is 213. So let's find the difference between these. So 24 minus 13 is 11. So my residual here is 11. And I can do that for all of these, just subtract. 9 minus, so 4 minus 9, negative 5. 8 minus 21, negative 13. 25 minus 32 minus 25, 7. Okay, so let's square each of these and add them up. By the way, that's if you look at the area of these, that's the same as the square of this. So, length times width. Well, let's say this guy. This is 11, so this is 11, and it's a square. So 11 by 11. Oh, the area of this square is length times width. So, or it's a square, so it's 11 squared. And let's add up all these areas of these squares. So the sum of the squares of the residuals is -5 squared plus 11 squared plus -13 squared plus 7 squared, 354. So we're trying to minimize the sum of squares, or the sum of the squares of the residuals. Now, let me plot the residual. Let's do the residual plot. So my residual plot will be the corresponding x value, 1, and the residual. Corresponding x value, 2, and the residual, 11. The corresponding x value, 4, residual, -13. Corresponding x value, 5, and the residual, 7. And so this is my residual plot. So that's what my residual plot looks like. So the residual plot is the graph of the points x, comma, y minus y hat. In other words, x, comma, the residual e. When analyzing a residual plot, look for a pattern in the way the points are configured and use the following criteria. The residual plot should not have any obvious patterns, not even a straight line pattern. This confirms that the scatter plot of the sample data is a straight line pattern. Okay, so this does not seem to have any sort of pattern. The residual plot should not become thicker or thinner when viewed from left to right. This confirms the requirement for different fixed values of x, the distribution of corresponding y values have the same standard deviation. Yeah, okay, that looks good. So this is for this. Now let's look at the shoe print and the height data are used to generate the following residual plot. So here's what my residual plot looks like. Look at this. So this residual plot becomes thicker. So that means that this is not satisfied. And so the requirement of equal standard deviations is violated. So let's look at the following residual plots. And so here's my residual plot. And well, it looks good. So the residual plot suggests that the regression equation is a good model. So this looks like, yeah, it's a good model. Next. This is not good. So this is not a good residual plot. If you look here, this has an obvious pattern. And so this, I can almost draw the equation. I can draw the equation for it. So this has the residual plot has obvious pattern, suggesting that the regression equation is not a good model. Okay, so it's not linear. The data is not linear. Next. This violates the assumption of equal variances. So the residual plot becomes thicker, suggesting the regression equation is not a good model. So no, not a good model. Okay, so complete regression analysis. First, construct a scatter plot. Verify that the pattern of points is approximately a straight line pattern without outliers. If there are outliers, consider the effect by comparing the results that include the outliers to the result that exclude the outliers. And of course, if there's an outlier that you suspect to be an error, get rid of delete that outlier. Construct a residual plot and verify that there's no pattern, and also verify that the residual plot does not become either thicker or thinner. Use a normal quantile plot to confirm The values of the residuals have a distribution that's approximately normal, and consider any effects in the pattern over time. Okay, so any questions on section 10.2?
Yeah, I'm not so sure what you mean by thickens when it just means
Say
like,
again.
what do you mean by thickens? Like when it gets, because I just, yeah.
Look at this. See how this is going further and further. These guys are going further and further apart.
Oh, okay, like they're going further apart from each other. Okay, got it.
Yeah. See how it's going like this, or
Okay.
if it looked like this, the
Mhm.
the dots kind of look like this. Then
Okay.
no, these don't have equal variance. So that's what I mean by becoming thicker. Okay.
Okay. Thank you.
Okay.
They don't call that diversion.
Well, yeah, but it's a residual, but it's a residual plot. So it's because it's not. So you can sort of thinking that, yeah, what happens is, you have a line, and the data looks like this. Yes, what's happening is that that they start out close, but then they start to quote unquote diverge out. So yes, but we don't call it that. But yes, I can see why you're saying that. It does sort of diverge out from the from this regression line. It's or but it could also go the other way around. It could be that they start out, but then it becomes better and better over time. But again, that's bad. So they could quote unquote converge to it, but that still is just as bad. So because again, the assumption of equal variances is not satisfied. So either converging or diverging, somehow changing this sort of it's the that they're getting closer and closer, quote unquote, to the line, or further and further apart, is not good. Okay. Any other questions? Basically, any sort of pattern other than the straight line pattern is not good. Okay. Let me go on to section 10.3. Section 10.3, the prediction interval and variation. So up until now, we've been doing the only sort of interval estimates we've been doing so far have been called, so the only interval estimates we've been doing so far are confidence intervals. And so an interval estimate of a parameter is a confidence interval. And that's what we've been doing so far. What's the confidence interval for estimating the true population mean, or whatever, the true population mean, et cetera, et cetera. But an interval estimate of a variable is called a prediction interval. And so, the only interval estimates we've been doing previously were our confidence interval. Actually, the only time we're going to diverge away from this is when we are doing in this section, where we're doing interval estimates of variables. And so again, they call those prediction intervals. Okay, so we will require that for each fixed value of x, the corresponding y values are normally distributed about the regression line, and they have the same variance. So my prediction interval for estimating y is, well, the predicted value of y plus or minus some margin of error e for a fixed x0. The margin of error is t, the t critical value, with degrees of freedom, nu equaling n minus 2, times the standard error for the standard error estimate, times the square root of 1 plus 1 over n, plus n times x0 minus x bar quantity squared over n, times the sum of x squared minus the sum of x quantity squared, where my standard error estimate is the square root of y minus y bar squared over n minus 2. So if we use the 40 pairs of shoe print lengths and heights and construct a 95% prediction interval for the height, given that the shoe print length is 29 centimeters, we get the following. And so y is equal to, the predicted value of y is equal to 80.9 plus 3.22x. We did that in the last section. Let's say x0 is equal to 29.0. And actually, if you looked on the output, they also told us the standard error. So the standard error was 5.943761. Plug in an x here. We got that the predicted value of y was 174.3. 40 minus 2 is 38, so degrees of freedom is 38. Let's say that alpha here is 0.05 and two-tailed, because every confidence interval, every prediction interval is two-tailed. So it's always two-tailed. And so we get, well, that the 95% prediction interval is from 162.087 to 186.451. And so this is 20 centimeters different. So, this is a large range of values. So the single shoe print doesn't give us very good information about someone's height. It's the explained and unexplained variation. So first, let's assume that we have a linear correlation. And let's say in this case that the predicted y value is 3 plus 2x, and that the mean of the y values is 9. And suppose we look at one of the values here. The sample data is x is 5 and y is 19. Then if you plug in 5 here, you get 10 plus 3 is 13. Okay, so I have that, again, if you plug in 5, you get y is 13. So my residual, my error, is 19 minus 13, 6. The mean is 9. 13 minus 9 is 4. And so 19 minus 9 is 10. So my total deviation is 10. That's how much my particular data point varies from the mean. So that's the total deviation from the mean. So the total deviation for the mean is 10. Next, this distance here from, well, let's do it here. This distance here from the predicted value to the mean, 4, is called my explained deviation. So my explained deviation is the difference from the predicted value of y and the mean of y. The unexplained deviation is therefore, well, your total deviation minus your explained deviation is your unexplained deviation. It is, well, these cancel. It is the difference between your data point and the predicted value of y. And so the unexplained deviation is what we called our residual. And we want to minimize the square of the unexplained deviations. So the total deviation is the unexplained deviation plus the explained deviation. Well, the total deviation is the explained deviation plus the unexplained deviation. The total variance, the total variation, is the sum of x minus x bar squared is the explained variation, the sum of y hat minus y bar squared, plus the unexplained variation, the sum of y minus y hat quantity squared. The coefficient of determination is the amount of variation in y that is explained by the regression line. It is the square, so not only is this the notation for the coefficient of determination, it's also the square of Pearson's product moment linear correlation coefficient. So it really is R squared. So R squared is the ratio of the explained variation over the total variation. The value of R squared is the proportion of the variation of y that's explained by the linear relationship between x and y. So if we use the 40 paired shoe lengths and heights in from Appendix B, we find the linear correlation coefficient to be 0.813. The coefficient of determination is therefore the square of this, 0.661. We can thus conclude that 66.1% of the total variation in height can be explained by the shoe print length. The other 33.9% cannot be explained by the shoe print length. So a lot of times you'll hear sort of, when you're watching the news or whatever, they'll, especially when they're interviewing someone, they'll say, well, we can determine that, that 50% of this is caused by whatever. And what they're doing is, well, they're doing this. And so they're looking at R squared. They're looking at the coefficient determination. So again, the total deviation is just y minus y bar. It's the deviation from the mean. The explained deviation is the deviation of the predicted value from the mean. The unexplained deviation is the deviation from the actual value of y and the predicted value of y. And again, the coefficient determination is the explained variation over the total variation. The standard error, the estimate, well, we did some of this, is the square root of the sum of y minus y hat squared over nu. It is the square root of the sum of the square of the residuals over your degrees of freedom. It is s of yy minus the square of s of xy over s of xx, all divided by nu. It is s of y times the square root of n minus 1 over nu times the square root of 1 minus r squared. It is the square root of the sum of y squared minus b0, sum of y minus b1, the sum of xy over nu, where nu is n minus 2. So the prediction interval for y, for which x is equal to x0, is the predicted value of y hat, plus or minus e, where e is equal to t times the standard, your standard error, estimate of your error, times the square root of 1 plus 1 over n plus n times x0 minus x bar squared over n times sum of x squared minus sum of x prime squared, where nu is equal to n minus 2. The confidence interval for beta 0 and beta 1. So now notice, so these are numbers, not variables, so it's a confidence interval. This is a variable, y, so it's a prediction interval. So the confidence interval for beta 0 is b0 plus or minus e. So again, the best point estimate for your population. This is b0's intercept. For the intercept is the sample intercept. Plus or minus e, where e is equal to t, the t critical value, times standard error, times the square root of 1 over n plus n, x bar squared over n, sum of x squared minus sum of x prime squared. The confidence interval for beta 1 is, again, b1 plus or minus e, where e is equal to t times your standard error, s of e, square root of n divided by n times sum of x squared minus sum of x prime squared, where nu is equal to n minus 2. The confidence interval for mu sub y, for all values of y for which x is equal to x0, is y hat plus or minus e, where e is equal to t times s of e times the square root of 1 over n plus n x sub 0 minus x bar squared over n, sum of x squared minus sum of x prime squared, where nu is equal to n minus 2. Any questions about this section? Okay. Multiple regression. Section 10.4. Multiple regression. And so a multiple regression equation expresses a linear relationship between a dependent variable and multiple independent variables, x1, x2, x3, x of k. The general form of a multiple regression equation is y hat equals b0 plus b1x1 plus b2x2 plus b sub k xk. So now it makes sense. So now their notation makes sense. So when they said, if you only had one independent variable, x. So now it makes sense that, y bar is, that y hat is b0 plus b1x, because it was part of this. So now the notation makes sense, why you put the y-intercept as b0 and the slope as b1, because it was part of this idea of a multiple, when you have notation for a multiple regression. So n here is the sample size. K is the number of predictor variables. Y hat is the predicted value of y. And again, x1, x2, up to xk are the predictor variables. The multiple coefficient of determination R squared is a measure of how well the multiple regression equation fits the sample data. A perfect fit would be when R squared is equal to 1. The adjusted coefficient of determination is this multiple coefficient determination modified to account for the number of variables and the sample size. So, table 10.4 includes a random sample of heights of mothers, fathers, and daughters based on data from the National Health and Nutrition Examination. Find a multiple regression equation in which the response variable y is the height of the daughter and the predicted variable x are the height of the mother and the height of the father. Okay, so we have here, height of a daughter, and we want to predict the height of a daughter from the height of the mother and father. So daughter is 58.6, mother's 63, father is 64, height of the daughter is 65.4, height of the mother is 65, height of the father is 68. So we get the following regression equation that the height of the daughter is 7.5 plus 0.707 times the height of the mother plus 0.164 times the height of the father. R squared is 67.5%, 0.675. They also give us an adjusted R squared. So the adjusted coefficient of determination is the multiple coefficient of determination R squared modified to take account for the number of variables and the sample size. So the adjusted R squared is 1 minus n minus 1, it is a sample size, divided by n minus k plus 1, k is the number of predictor variables, times 1 minus R squared. So let's do this. So the adjusted R squared is 1 minus sample size. Sample size, they should tell you here. Well, sample size is 20 because that's 19. They don't tell it here. You'd have to, so 2, 4, 6, 8, 12, 14, 16, 18, 20. Okay, so sample size is 20. Number of variables, oh, there's 2, mother, father. And R squared was, well, 67.5%, 0.675. Plug it into your calculator, you get 0.637. So 63.7%. Ah, we got the same thing. Good. So when we compare multiple regression equations to other multiple regression equations, it is better to use the adjusted R squared of 63.7%. The p-value, in this case 0, is the measure of the overall significance of the multiple regression equation. So the p-value of 0.000 is small, indicate that it's in the rejection region. And so since we're in the rejection region, we reject the null hypothesis of no correlation, meaning that there is some correlation. And so that indicates that the multiple regression equation has a good overall significance and is usable for predictions. So long as we draw the graph first and see if there is a linear relationship. So first you should graph the line, graph all the data, and see if it does look like it is linear. And then, given the p-value of 0, we would then say, yeah, this is usable for predictions. So it makes sense to predict the height of daughters based on the heights of mothers and fathers. So the value 0 results from the test that both beta 1 is 0 and beta 2 is 0. And the alternative hypothesis is that they're not both 0 and alpha is equal to 0.05. Okay, so in this case, I rejected the null hypothesis. So one of them's not, at least one of them's not 0. Okay, good. So, that indicates again the equation is effective in predicting heights. So, finding the best multiple regression equation. So, use common sense and practical consideration to include exclude variables. Consider the p-value. Select equations whose overall significance is determined by the p-value that have small values. And so rejecting the null hypothesis. So the smaller ones, the smaller the value of p, quote unquote, the better. Consider equations with high values of the adjusted R and try to include the fewest possible number of variables. So with the following criteria. If an additional predictor variable is included, the value of the adjusted R squared does not increase by a substantial amount, then you should get rid of that because, get rid of the one that has the additional predictor value. For a given predictor of X variables, select the equation with the largest adjusted R squared. In weeding out the predictor variables that don't have much effect on the response variable X, it might be helpful to find a linear correlation coefficient R for each of the paired variables being considered. Okay, so let's do this. In data set 2, in Appendix B, includes age, foot length, shoe print length, shoe size, height for 40 differing pairs of subjects. Use the sample data to find the regression equation that is best for predicting height. So I've got a whole bunch of variables. How many how many of these variables should I use to predict, to best predict the height? And so, the following table includes the key results from combination of the 5 predictor variables. Okay, so let's look at this. Okay, so first off, I look here and the p-values are all small. Good. Except this p-value is not, is a little bit bigger. So I don't get rid of this yet. But I just sort of notice, okay, this is a little bit, see, it's still significant. So it's still okay. So all of these p-values are okay. So I'm going to let everything go. Not eliminate anything yet. Do the p-values. Now, let's look at the adjusted R squared. First off, there's one obvious one to get rid of. So I'm going to get rid of this guy. Maybe I'll change pink. let's get rid of this guy. Because this is really small. So compared to everything else, all these are basically around 0.7. This is 0.1. That's too small. So get rid of that guy. So that guy's gone. Okay, so now let's look at the other ones. So I have here 4, 1, 2, 3, 4 variables. I have here 1, 2 variables. Okay, so I look at this guy and this guy. Let's compare these two. Okay, so let's compare these. I look at my adjusted R squared, 0.7484, 0.7585. Okay, so I added 1, 2, 1, 2, 3, 4. I've added 2 additional variables, age and shoe size. I added age and shoe size. And when I did that, it barely changed. I almost didn't change at all the adjusted R squared. So let's get rid of this guy because it didn't make that big of a difference. So let's get rid of this guy. Okay, so that guy's gone. Okay, because the other cases with fewer variables just about had the same adjusted R squared. Okay, so now let's look at this guy. So now this is 2 variables as compared to 1 variable. Again, this didn't change. It went from 0.7 to 0.74. It's not that big of a difference to really count as significant. So let's get rid of this guy. Because again, there wasn't that much of an improvement from going to justify having an additional variable. Now I look at what's remaining. 1 variable, 1 variable. Well, this is obviously bigger than this guy, so that's better. So get rid of this guy. So what's left? Well, there's only 1 guy left. So now it has the best adjusted value of R squared for the fewest number of variables. So this guy's a little bit higher, but look, we got instead of 1 variable, I got 1, 2, 3, 4 variables. So it didn't help that much, and so get rid of those additional variables. The more variables you put in, the more sort of variation, and the worse the sort of prediction is going to be. So don't try to do it with the fewest number of variables as possible. So in this case, we should only use foot length. So I should only do foot length. So foot length is really the only one that should be there. Actually, it turns out that foot length and shoe print length, those should be about the same. So these actually should be just about the same, but okay, so dummy variables. Okay, so if you have some qualitative variable, you can, and it's, let's say, it only has a few values, you can include, a dummy variable just to indicate whether you want to use that variable or not. And so 0 would indicate failure, 1 would indicate success. And so 1 would indicate that we're going to use, so let's do the following. I'll do it. So let me show you an example of what you should do. So the data in the following table includes a dummy variable for sex. So they included 0 for female and 1 for male. So success is being a male. So being male is success, and being a female is a failure. It's because you're looking at height. So height, usually males are taller than females. So probably the success should be male, so that you don't have some negatives. Okay, so that's really just for the sign. It doesn't really matter. I could have done the other way around. Of course, the equation would be different, but just slightly different. It just changed really the sign, one of the signs for this equation. Okay, so given that a mother is 63 inches tall and a father is 69 inches tall, find the regression equation and use it to predict the height of a daughter and a son. So here are the heights of mothers, fathers, whether they are male or female, and the height of your child. Okay, so we do a regression equation. Again, do multiple regression on this. Coding these as 1s and these as 0s. We then get the following regression equation. 25.6 plus 0.377 times the height of the mother plus 0.195 times the height of the father plus 4.15 times the sex. So let's find the height of a daughter. So sex in this case is 0. The mother's height, we said, was 63. And the father's height is 69. And so let's plug in. So 25.6 plus 0.377 times the height of the mother, 63, plus 0.195 times the height of the father, 69, plus 4.15 times the sex, which is 0. So 62.8 inches. So we predict that a daughter will be 62.8 inches tall, 5'3", basically. Next, let's do the height of the son. And so the height of the son is, well, 1, let's plug in. So it's 26.5 plus 3.77. Again, the mother is still 63 inches tall, and the father, and plus 0.195. Again, the father is still 69 inches tall, plus 4.15. Again, this is for the your brother, and so that'll be a 1. So 67 inches tall. So the son is 67 inches tall. Any questions about this? So a lot of times we add these dummy variables to indicate things. Okay. Any questions on section 10.4? Okay. Let me go on to section 10.5. Section 10.5, nonlinear regression. And so, linear regression, well, looks like a line. Y equal 1 plus 2x. Quadratic, well, it looks like a parabola. Say y equal 2x squared minus 8x plus 9. Cubic, looks like the sigmoidal. I just said in general, y equal ax cubed plus bx squared plus cx plus d. I just drew it freehand. I didn't have a real equation in mind. Quartic. Y equal ax to the fourth plus bx cubed plus cx squared plus dx plus e. It looks something like this. Logarithmic. Y equal a plus b ln x. So something like y equal 1 plus 2 ln x. Looks like something like this, logarithmic. Exponential. C is equal to kx, or sometimes we write it as c equal e to the x. It's the same thing. Here, I guess they wrote it this way. Y equal 2 to the x. Power function, y equal a x to the b. So let's say y equal x squared. So these are examples. Oh, logistic. Y equals c divided by 1 plus a b to the minus bx. Y equals c over a 1 plus a e to the minus bx. So it would look something like this. So, table lists the population of the United States for different years. So find a mathematical model for the population size and predict the size of the US in the year 2020. Okay, so I have here 1800, 5 million. Year 2000, 281 million. And so they code these as 1800 is 1, 2000 is 11. So every 20 years, they add 1. Okay, so let's do this. So I have some of the results here, but let me actually do this and figure out what's going on here. Okay, so let me put all this data into my oh, I've got to stop sharing. Okay. So let me put this data in here. Okay, so let's put in, I don't think I'm going to do this just because I'm lazy. Sequence of 5. Okay, so let's do x. And my variable is x. I'm going to start at 1 into 11. My step size will be, 1. And let's store this in L1. So I'm just lazy. It gives me the sequence 1 through 11. Okay, I could have just done it by hand, but I'm too lazy. Okay, so let's put in the numbers 5, 10, 17, 31, 50, 76, 106, 132, 179, 227, 281. Okay. And let's store that in L2. Okay, so let's do a, so first off, Let's get rid of all my graphs. Let me just see, this is plotting everyone. That looks fine. The window, let's see. So let's go from 0 to 12. And yeah, I'll go from 0. I'll go from 0 to 290. Okay, let's see what my graph looks like. Voila. So this is what my graph looks like. Oh, okay. So that's the population of the United States. Okay, so first off, let's do a linear correlation. So let's do some linear regression here. Doesn't really matter which one I do. X1, Y1, yeah. Okay, good. R squared is 0.9245459409. Okay. And now let me go to Y and let me input my variable, variable, and go down to statistics, go down to the equation, regression equation. Okay. Let me graph this. Oh, that's horrible. So it doesn't look like a line. If you look at that, it certainly doesn't look, that this data is on a line. Okay, so now let's go to the next one. Let's go to quadratic. Let's quit out this. Let's go to stat, calc. What's the next one down? Quadratic. Let's do quadratic. Okay, so here's quadratic. Okay. And so R squared is, R squared is much better. And so R squared here is 0.9991688,446. Okay. So now let's go to Y. Let's put the next one down. So let's go to variables, statistics, and do the regression equation again. So now if I do that, when I graph it, oh, look at that. That second one looks so much better. Let's get rid of the first. So let's get rid of. So this first guy is not good. So I'm just going to get rid of that first guy. So linear is certainly out of the just out of the running. So I'm going to get rid of linear. So linear is just not in the running. Quadratic is possibly in the running. So quadratic doesn't look too bad. So if you look at this, actually, it looks pretty good. There are a few that are slightly off, but not bad. So quadratic looks pretty good. Okay, so let me go to quit this. Oops. Let's go to I did quadratic. Let's do cubic. Let's go to cubic. Let's do cubic next. R squared is, that's not too bad. So for cubic is 0.999418429. Okay, so that's not too horribly bad. So let's look and see what it looks like for the second one. And I guess I'll put in vars. And fifth one down and regression. Okay, so let's cubic. Let's look at the cubic. Looks just about the same. So cubic is still okay. So cubic is okay. Let's look at quartic. So let me go to the quartic. Okay, so let's look through quartic. Good. And let's, R squared is 0.994670886. Okay, just about the same. That's okay. Let's graph this. So now for the quartic. Let's graph that. Again, it looks pretty good. Not too bad. Okay, so it still looks pretty good. Quartic. Let's go to logistic. And so I did quartic. Oh, I can do linear regression. Let me do linear regression. Oh, no. That's logarithmic regression. I'm sorry. That's logarithmic regression. I said linear. Let's do logarithmic regression. 0.69. So R squared is 0.6961. Oh, that doesn't look good. Okay, so that doesn't look that good. Let's go to y equals. Let's see what happens. Vars, the fifth one down, equation. And so graph this. Oh, it's not even close. It looks like the polar opposite of what should happen. So I'm going to get rid of this guy. So this is completely out of consideration. So logarithmic is out of consideration. So I'm not going to, and certainly R squared was out of the ballpark. It was 0.69. It was out of the ballpark. Okay, so let's quit out of this. So I did logarithmic, exponential. Let's do exponential. See what happens. Okay, so exponential R squared, small, 0.963, which compared to all the other ones is not that good. Well, not so good. Okay, so let's go to y. And let's do exponential. And let's see how it looks. Oh, uh-oh. Doesn't look good. It doesn't look good. So we're going to get rid of that guy. So this certainly doesn't look good. Okay, so get rid of the exponential. That's out of that's not in the running. Nope, get rid of that guy. That's not in the running. So let's see. I did exponential power logistic. I don't think I did power yet. Let's do power. R squared 0.9764. Okay, so not too bad. Let's go here and see what happens with the power. Okay, so let's look at power. Again, the power is not doing well. So get rid of the power. Power is not in the running. Only degree 2, 3, and 4. So quadratic, cubic, and quartic are the only ones that at least semi-fit my model. Okay, so none of those worked. And then lastly is, oh, we could do sine. That's going to be horrible. Let's do logistic. And so, oh, it doesn't tell me my R squared. Okay, logistic. And let's graph this. Let's see how logistic works. It's not horrible, but it's not as good as the rest of it. If you look at this, you can see that this is out of alignment. It's compared to everyone else. So it's more out of alignment than the others. Okay, so not as good. Let's keep it for a while. And then let's see if anything else left. Oh, the sine. I don't even know if I can do sine. Let's see. You have to do it in, certainly sine is never going to work. So sine, iteration 3, period. It's never periodic. Okay, so oh, it actually converged. Okay, so let's see what this is. It's not gonna. I don't have a lot of faith in this one. 5. And let's look at this. Actually, it wasn't horrible. Wasn't horrible. Of course, I made it the period gigantic. Okay, so if I look here, I guess the only ones in the running were quadratic, cubic, fourth degree, logistic, so quartic, something in the logistic, and sine. Okay, so first off, if I look at, well, we don't know for either of these. They didn't calculate the R squared, so they didn't calculate R squared for us. I would imagine so. The 9992. So the quadratic, the R squared is 9992. Good. Next, cubic is 9994. So adding one additional term barely changed R squared. So get rid of this. Doesn't work. Look at the quadratic. The quartic gives us R squared is 0.9995. Again, just barely changing R squared. You had to have additional 2 terms. Get rid of it. Doesn't make a big of a difference. Unfortunately, these guys, I don't know what R squared is for these. But they're more variables. So there are more variables. So let me just look. So the pink is definitely gone. The pink is definitely gone because you're looking at that's furthest from the data. Both of those are actually the same. Oh, because I did a weird slide. It's not sinusoidal. I know that the growth of you don't get periodic motion in a so just due to the fact that I sort of cheated, I gave a gigantic, just so that it would converge. I gave a gigantic value of the period so that I could converge this thing, because otherwise it would never converge. Yeah, it had to have a. Yeah. Okay, so I had to have a weird sort of criteria in order for it to convert. This also really should be thrown out because it's never going to be sinusoidal. So really, the best predicted value here is of how the value of what. Oh, I shouldn't have gotten rid of the other ones, but the predicted value of what the size, the population is. The U.S. should be quadratic, so it seems like it's quadratic. You could also, let's see, table. I want to figure out the population in the year 2020, so 12. 336 million, 410,000. So that's the predicted amount. Okay, so actually, if 336, yeah. Okay, so let's see. Okay, good. Let's actually look. Okay, so let's look here. So any questions about, so far, what I did on the regression equation? Yeah, something of that sort. Yeah, so 62, right. So that's R squared is 0.92. Yes, I think so. I think that's what I got. For linear, let's see. I don't have to split over to look at you. Okay, so it was linear. Yeah, negative 61.93. Correct. That's what I got. And that is correct. And if you do linear in the year 2020 for linear, I got rid of the linear for some reason. Well, because I got rid of the linear one. Yeah, for my predicted value for the linear. Yeah, that's what it looks like. So notice, because it's so far off, I got rid of the linear guy. So I didn't actually do the predicted value for linear. I did the predicted value for the other ones. So doing the same thing I did, of course, I didn't get rid of them. So quadratic was 336, cubic 342, quartic 347, the logistic 323. Okay, so what was the actual value in the year 2020? So population of the United States in the year 2020 is 330 million. Oh, okay, so 330 million. So here, so it's less. So the question is, well, what happened to the other 6 million people? So why are there 7 million people less in the year 2020? So what happened to the 6 million people or 7 million people? So there's 7 million people that are missing. Why? Why are there 7 million people less than what we predicted?
Well, it doesn't count the immigrants. It won't count the
Yes.
asylums. It doesn't count
No. Oh, no.
illegals.
So the fact is, what you said is that there are less immigrants into the country.
Yeah.
So prior to 2014, 2015, there are more immigrants coming into the country. And so they actually so your population figure, what you notice is that what do you consider someone, what is a population? And so that's a really big sort of criteria. Usually they go with the UN definition. There's a definition given by the UN of what a population is for a country. So usually they use that criteria of what do you consider, quote unquote, a population, which may not always be the given number that is given by a country, because sometimes they give different things and they also give the UN definition. But yeah, so one is, as you said, there are less people because less immigrants. So less immigrants into the US. What else? Why else are there? So why are there 7 million? There's 7 million people that are missing. So some of those 7 million were due to less immigrants, not all the 7 million. What else? What other things would cause 7 million people to disappear? Anyone else? Anyone else?
It could be the tightening of the border, so there is no more.
Yeah. So the immigrants, yeah. So less immigrants. So that was one of them. Having less immigrants. Oops, here it is. Less immigrants. Pandemic. Yes, that's right. Oh, passing away. That is correct. So there's several things there. There are two things there that are correct. The average lifespan has been decreasing since 2000, from 2016 to 2021. The average lifespan has actually been decreasing, fueled by a few states. So there are a few states where there was a gigantic decrease in the average lifespan of people. So if you live in California, you have a much larger average lifespan than, let's say, if you live in Louisiana. I think it's like, is it 17 years? You live 17 years longer if you, maybe 20, so between 17 and 20 years longer if you live in California as compared to, like, say, Louisiana, Mississippi. So those states, in the last several years, their average lifespan has been dropping dramatically. So a lot of people in those I keep saying countries, in those states, the elderly have been dying at much larger rates than would be expected historically, and the pandemic. So there was also a pandemic going that also killed off another 1 million people. So there's another 1 million there. What else? So let's see, what else? There was also one or two other things. Oh, and no one passed away. There was also drug overdoses, an increase in drug overdoses. And so, does anyone know where in this country was there a gigantic increase in deaths due to drugs? Does anyone know? It was quite dramatic. A lot of people were dying. Does anyone know? Especially with fentanyl, the oxycodone and fentanyl. Where's the crisis in drugs in the U.S., where people are dying by tremendous amounts? New Mexico, no. Philadelphia, no. Not New Mexico. So where the increase has been in West Virginia. So so it's not in big cities. So Boston, Philadelphia, no, those are so you would get very few people dying in Boston, Philadelphia. No. Not New Mexico either. It is in Appalachia. It is that's also where they have the highest crime rates. So it's where they had, you have the highest crime rate, highest murder rates, things like Kentucky, Tennessee, the highest, drug rates, deaths due to drugs and all that. So it's Kentucky, it's always, it's almost always Kentucky, West Virginia, Tennessee, those areas. Oh, yeah, yeah, yeah. It's those areas, yeah. That have Delaware. Not as much in Delaware. Not as much in Delaware. As compared to those other areas. Delaware, because it's small anyway. There's not as many people in those areas. Okay, so yeah, so that's where mostly the 7 million people have gone. So the model was good. It's just that some unexpected things have occurred in some areas of the country, which is kind of strange. Why? Well, there is a reason why these areas of the country are uh, especially in lifespan, why the lifespan is so much less in particular areas of the country as compared to other areas of the country. And it's quite dramatic, actually. And the divergence has only been in the last few years, the last like 20 years or something, where it's really diverged and accelerated, where you have these disparate differences. Okay, so this is the predicted amount. Again, it's too high because of other things that are out of that would not be could not be modeled due to historical models. So these are historical models. If things change, that's different from history, then obviously they can't be they can't be modeled into this. And so that's why you shouldn't go too far in the future, because you don't know what happens in the future. Okay, so let's see. And this is just telling you how to do it on computers. Okay, any questions on section 10.5?
Yeah, can you scroll for a moment to the formulas, because the PDF shows errors. A little higher, where you describe the formulas, quadratic. Oh, yes.
These things. These
Yes.
things.
Yes.
Oh, okay.
Let me copy them, because on the PDF they are math processing errors, so they don't show.
Sure.
Let me see. This is.
And then tell me when to scroll.
Yeah. Thank you. Is the norm. Extends to plus the XC. Logistic logarithm.
Yeah, so there it is.
Explanation is to this C times K. And what else is and the logistics, please. Okay. So it's E.
Yeah, it's e to the negative b x.
Thank you. Thank you.
Okay. Okay, then. Any other questions? Delaware. Yes. Okay. Okay, so that finishes off chapter 10. Good. Let me start chapter 11. Goodness of fit and contingency tables. So section 11.1 is on goodness of fit. And so a goodness of fit test if the observed frequency distribution conforms to that of an expected frequency distribution. Particular types of goodness of fit tests will be, well, a test of independence, which we'll be doing later in this section or next section? In the next section. Test of independence will test if variables are independent, if there is no association between two variables. A test of homogeneity, test if different populations have the same proportion of successes. And so, let me give you some notation. O represents the observed frequency of an outcome, and this is found from your sample data. E represents the expected frequency of an outcome, found by assuming that the distribution is whatever has been claimed it is to be. K represents the number of different categories, the number of different cells. N is the total number of trials. We will assume that the data is randomly selected and that it consists of frequency counts for each of the different categories. If I'm going to be using some asymptotic method, then for each category, the expected frequency has to be at least 5. Otherwise, you can't use an asymptotic method. My hypothesis test. The null hypothesis is that the frequency counts agree with that of the claimed frequency distribution. The alternative hypothesis is that the frequency counts do not agree with that of the claimed frequency distribution, the expected frequency distribution. And let alpha be a level of significance. If we have that each of the expected values for each of the categories, for each of the cells, is greater than or equal to 5, then I can use an chi-squared approximation for the hypergeometric distribution. And so the test statistic for this asymptotic technique, this asymptotic estimate, is that chi-squared is equal to the sum of O minus E quantity squared over E. It is, and I simplify this, to the sum of O squared over E minus N, where my degrees of freedom are equal to K minus 1. So notice, not N minus 1, but K minus 1. It's the number of categories minus 1. It's not the sample size minus 1. So notice something completely different. So I just look at the number of categories minus 1, and that gives me my degrees of freedom. So again, we call chi-square. So gamma is the area under the curve from 0 to infinity, for x is between 0 and infinity. For the curve x to the power t minus 1 times e to the minus x. Again, gamma of n is just n minus 1 factorial. So gamma is just a extension of the idea of a factorial to the real numbers, the complex numbers. The chi-squared distribution has a probability density function of chi-squared to the power of nu over 2 minus 1 e to the minus chi-squared over 2 sigma squared, divided by 2 to the power nu over 2 times sigma to the nu times gamma of nu divided by 2. The expected value chi-squared is nu. The variance of chi-squared is 2 nu. The mode is nu minus 2, and the skewness is radical 2 over nu. We had the chi-squared approximation for z, for the z chi-squared approximation, the Wilson-Hefferty approximation, that chi-squared is equal to nu times the quantity 1 minus 2 over 9 nu plus z radical 2 over 9 nu quantity cubed for degrees of freedom be greater than or equal to 5. We also had the chi-squared approximation for z, the Wilson-Hefferty approximation. Z is equal to the cube root of chi-squared over nu minus the quantity 1 minus 2 over 9 nu divided by the square root of 2 over 9 nu for degrees of freedom being greater than 5. In other words, the cube root of chi-squared over nu is approximately normally distributed with mean 1 minus 2 over 9 nu and standard deviation the square root of 2 over 9 nu. So, finding the expected frequencies. If all the expected frequencies are assumed to be equal, then it's just n divided by k. If they're not assumed to be equal, then it's just np. And so, well, we call a multinomial experiment for a fixed finite number n of independent trials with k outcomes with probability p1, p2, dot, dot, p sub k, where p1 plus p2 plus dot, dot, p sub k is equal to 1. A random sample of 100 weights of California is obtained. The last digit of those weights is summarized below. When obtaining weights, it is extremely important to actually measure the weights rather than ask a person to self-report them. By analyzing the last digit, we can verify the weights were actually measured, since reported weights tend to be rounded to something in either 0 or 5. Test the claim that the sample is from a population of weights in which the last digit does not occur with the same frequency. And so there are 46 zeros, 3 nines. Okay, so seems to be a lot of these numbers, a lot of these digits. So let's do this. Well, the data comes from randomly selected subjects. The data consists of counts. You're counting how many. With 100 sample data, values, and 10 categories that are claimed to be equally likely, the expected value of each is 10, which is greater than 5. So I can use an asymptotic method. Okay, so the null hypothesis is that the observed frequency distribution conforms to that of a uniform distribution, because, well, that's what it said, that they occur with the same frequency. The alternative hypothesis is that the observed frequency distribution does not conform to that of a uniform distribution. Let alpha equal 0.05. Okay, so since each of the expected frequencies are 10, which are greater than 5, then the asymptotic chi-squared method is applicable. And so we're going to be using a right-tailed chi-squared test. So my observed is, well, 46 zeros, 3 nines. Add them all up to get 100. My expected are, well, we have 100 and there are 10 digits. So 100 divided by 10 is 10. So I expect if all of these digits are expected to be at the same frequency, then they should all have a frequency of 10. So there'll be two ways that I can compute the test statistic. Oh, I should, before I do that, if I look in my table for chi-squared, my degrees of freedom is 9, and alpha is 0.05. And so, actually, I remember this number. So I get chi-squared is 16.919. We've done this evidently several times. Look this number up in my table. Okay, so I can compute the test statistic doing one of two ways. I can do observed minus expected, 46 minus 10, 3 minus 10, square it, 36 squared, 1296, negative 7 squared, 49, and divide by the expected, 10. 1296 divided by 10, 129.6. 49 divided by 10, 4.9, and add up all these. 212.8. Or I could do the following. So rather than doing all this, I could just take the observed, square it, and divide by the expected. So 46 squared divided by 10, 211.6. 1 squared divided by 10.1. 2 squared, 4 divided by 10.4. 3 squared, 9 divided by 10.9. 3 squared, 9 divided by 10.9. 30 squared, 900 divided by 10, 90. 4 squared, 16 divided by 10, 1.6. 0 squared, 0 divided by 10, 0. 8 squared, 64 divided by 10, 6.4. 3 squared, 9 divided by 10.9. And add these up. 312.8 minus 100 gives me 212.8. Same answer, same test statistic. This test statistic is in the rejection region. Therefore, I reject the null hypothesis. Since I rejected the null hypothesis, it does not conform. So no, there's insufficient evidence to reject the claim that the last digits do not conform with the same frequency, do not occur with the same frequency. And so it was not measured. It was obviously self-reported data. Since my test statistic was in the rejection region. So again, a multinomial experiment has a fixed finite number of trials, n, that are independent. The outcome of each trial is classified into exactly one of k several different categories, and the probability of each of the different categories remain constant for each trial. So let's do this. Again, goodness of fit test is used to test the claim that observed frequency distribution fits a expected frequency distribution. And given that the expected frequency is at least 5 for each category, then I can use the asymptotic method. We can approximate a hypergeometric distribution by chi-square distribution. And I have the chi-square is equal to, I'm going to just use this one, the sum of the observed squared over the expected minus n, where my degrees of freedom is k minus 1. Okay, so let's do this. Last year, the student body of a community college consists of 85% white, 10% black, 5% others. This year, a random sample of 300 students consists of 243 white, 54 Black, and 3 other students. Tested composition, whether the composition student body this year fits last year's composition. Let use alpha equaling 0.025. Okay, so, well, data comes from randomly selected subjects. Data consistent counts. Eventually, we'll show that each expected frequency is greater than 5. So we can use the asymptotic chi-squared method. So we haven't shown this yet, but we will in a minute. So the null hypothesis. This year's frequency distribution conforms to last year's frequency distribution. The alternative hypothesis. This year's frequency distribution does not conform to last year's frequency distribution. Alpha is 0.025. My number of categories, white, black, other, 3. Degrees of freedom, therefore, is 2. Alpha 0.025. So if you look in your chi-square table, you get a critical value of 7.378. Let's calculate my test statistic. So again, 243 white, 54 black, 3 other. So you add that up, you get 300. So we said that there were 10, so black is the easiest. They're 10% black. So what is 10% of 300? 30. So that's the easiest. They're 30 black. Next, 5% other, so half of the black is other students. So half of 30 is 15. So there are 15 others for a total of 45 out of the 300. So there are 255 remaining white. And so 255 whites, 30 black, and 15 other. Any questions about how I figured out the expected? Next, notice that each of these are greater than 5. So yes, indeed, this was a true statement. So yes, indeed, I can use the asymptotic chi-squared method. Okay, so now let's take, 243 squared divided by 255, 45 squared divided by 30, 3 squared divided by 15. Add them all up. 329.364,705.9 minus 300. 29.3647059. Okay. So that's my test statistic, which is in the rejection region. So I reject the null hypothesis. So I rejected the null hypothesis. So no. There's insufficient evidence to support the claim that this year's student body conforms to last year's student body composition of 85% white, 10% black, and 5% other. There are a lot more other. No. This is expected. There are a lot fewer other. And there are more black. So there's fewer other, more black, and a few less white. So there's more black. So I'd say not enough others, and a little bit too much black, and slightly, just slightly, too small number of white. Okay, and so it's not the same. Things have changed. The blacks were higher or they were lower? The blacks were higher. So the blacks were higher, the others were lower. Yeah, the others were lower, and the whites were slightly lower. So this went up. The blacks went up. Everyone else went down. So the blacks went up, and then these plummeted, and they took away a few of the whites also. Okay. The following data from a random sample recorded to investigate whether a horse's chance of winning a race in a circular track are affected by starting position in the starting lineup. The starting position 1 is closest to the rail on the inside of the track. And so starting position 1 had 14 wins, ... Starting position 8 had 30 wins. Use alpha equaling 0.05. So again, data comes from randomly selected subjects. Data consists of counts. We will eventually figure out the expected frequency, which is 19, which will be greater than 5. And so we'll use the asymptotic method. So let's construct my hypothesis test, and I'll sort of do it several ways. First, sort of a generic way. All goodness of fit tests, have a hypothesis test stated as follows. So, null hypothesis. The observed frequency distribution conforms to that of the expected frequency distribution. Alternative hypothesis. The observed frequency distribution does not conform to that of expected frequency distribution. Alpha is 0.05. Okay, all nice and fine. Now let's try to restate this, where we actually tell you what the expected frequency distribution is, so that I can do it mathematically. So I can actually calculate all of these, the E and the calculate the value of my test statistic, etc. So we formulate this hypothesis test as follows. The null hypothesis. The observed frequency distribution conforms to that of a uniform frequency distribution. The alternative hypothesis, the observed frequency distribution does not conform to that of a expected uniform frequency distribution. Alpha is 0.05. Okay, so this is how we're going to calculate, all of our test statistic and things involving the data. Let's reformulate it yet again. So it's, in the words of, in this case, a horse race. So let's reformulate it. So what does this mean? Well, observed frequency distribution conforms to that of a uniform, meaning no matter where you start, you have an equally likely chance of winning. Null hypothesis. Number of wins does not depend on its starting position. Alternative hypothesis. Number of wins depends on your starting position. Alpha is 0.05. So now, in the way I've stated here, I can now interpret what happens when we either, reject or we do not reject the null hypothesis. So this was the generic. So all goodness of fit tests are set up this way. Then in the particular case, we can rewrite it. And then in the words of the claim, we can rewrite it. So we're going to have since this is a goodness of fit test, so this will be a chi-squared right tail test. Since it's an asymptotic goodness of fit test, this will be a chi-squared right tail test. The number of categories, 8. So there are 8 of these starting positions. So therefore, my degrees of freedom is 7. If I look in chi-squared table, then my critical value for alpha equaling 0.05 and degrees of freedom equaling 7 is 14.067. So here are all my observed. If I add them all up, I get 152. There are 8 positions. 152 divided by 8 is 19. So each of these are equal to 19. I add these up. Notice I get the same number, 152. If it's different, then I did something wrong. Now let's do square the first column divided by the second column to get the third column. So 196 over 19, 144 over 19, 400 over 19, 169 over 19, 289 over 19, 625 over 19, 441 over 19, 900 over 19. Add them up. 166.5263158 minus 152, 14.5263158, which is in the rejection. The test statistic is in the rejection region. So I reject the null hypothesis. So yes, there's insufficient statistical evidence to reject the claim that a horse's chance of winning a race on a circular track are affected by its position in the starting lineup. Okay, next. An example. Die is thrown 120 times, and the frequency of the various faces are as follows. You roll 10 ones, 27 sixes. Test whether the die was fair, use alpha equaling 0.05. Okay, so data comes from random data. The data consists of counts. The expected frequency, which we'll determine, is 20, which is greater than 5. And so we can use the asymptotic method where we approximate my hypergeometric distribution by chi-square distribution. So my hypothesis test. Again, I'll write the 3 different ways of sort of writing down my hypothesis test. So again, the generic way of doing it for all goodness of fit test. Null hypothesis. Observed frequency distribution conforms to that of the expected frequency distribution. Alternative hypothesis. Observed frequency does not conform to that of the expected frequency distribution. Alpha 0.05. In this particular case, our expected frequency distribution is, well, die is fair. A die is fair when each of these, you roll the same number of 2s as you roll 4s, etc. And so we expect a uniform frequency distribution. So let me reformulate the hypothesis test as null hypothesis. Observed frequency distribution conforms to that of a uniform frequency distribution. The alternative hypothesis. The observed frequency distribution does not conform to that of an expected uniform frequency distribution. Alpha is equal to 0.05. Let's restate this as well. Conform to uniform frequency distribution means it's equally likely to roll any particular value of your die, meaning the null hypothesis, die is fair. Alternative hypothesis, die is not fair. Alpha is 0.05. So again, we're going to be doing a chi-squared right-tail test. In a second, we'll actually see that all of the criteria for a chi-squared approximation is applicable. And so we have here, there's 6 faces. Therefore, my degrees of freedom is 5. Alpha is 0.05. And so my critical value from my table is 11.070. My test statistic I'll use as being chi-squared equals sum of observed squared over expected minus sum of expected. And so observed 10, 15, 25, 25, 18, 27. You add these all up, you get 120 divided by 6. So each of these should have a expected frequency of 20. Each of these 6 categories should have expected frequency of 20, which is greater than 5. So yes, all these requirements are satisfied. Observed squared divided by expected, 100 divided by 20, 5, 225 divided by 20, 11.25, 625 divided by 20, 31.25, etc. It goes. And so add them all up, and you get 131.4 minus 120, 11.4. And so 11, my test statistic is in the rejection region. Therefore, I reject the null hypothesis. So I'm rejecting this. So, no, it's a loaded die. There's insufficient evidence to support the claim that the die was fair. They're not giving you a fair die. The following data are the number of words in 50 sentences selected at random from Christopher Darden's I Contempt. So 7 had 3 to 8 words. 2 had 28 to 33 words. Test whether the given distribution fits the normal distribution with mean 15.8 and standard deviation 6.96. Use alpha equaling 0.05. Okay, so data come from random data. The data consists of counts. We'll have to show that each expected frequency must be greater than 5. Well, we're going to actually force this to occur. So we're actually going to force this to occur. So let's start to do this, and then I'll show you how to force it so that this actually is satisfied. So the mean is 15.8, standard deviation 6.96. So I want to figure out first, well, what is the expected number of sentences that have more than 28 words. Okay, so, well, let's find the probability there are more than 28 words, and then multiply it by 50, assuming we have this normal distribution. So let's do this. I'll do this on my calculator. Let me do this on my calculator. Again, you could, oops. Oh, yes. So how quick? By Tuesday. So it's you know, so I would like these to be done by Tuesday. Okay. So you have a while to look them over and all that. Yes. Okay, so let me stop sharing. Let me go to the my TI-84. I could have done this one, but it doesn't matter. Okay, so well, let's get rid of that. Okay, so let's do 50 times normal CDF I'm going to go from 28 to infinity. The mean was 15.8, and the standard deviation was 6.96. Uh-oh, that's less than 5. And so 1.990590611. Now, I could also do, well, I know the area from the middle, from the mean, to the right of the mean is 0.5. So I could have also done it this way, 50 times 0.5 minus normal CDF. going from the mean, 15.8, to 28. You could also do that to get, well, actually what I wrote on the paper, 1.99059067. But again, that's too small. Okay, so that's just too small. So let's, combine. So I have also the 23 to 28. I'll combine that and say, let's go from 23 to infinity. So let's do that instead. So let's do this. And we're going to go from 15.8 to 23. Okay, let's see what I get. 7. Oh, good. So if I combine those last two groups together, I now get something that is fine. And so let me store that. Oh, let's call this L2. Let's store this in L2. Oops. In L2. Let's say in the 5th position. Oh, I should have cleared L2. Yeah, let me clear L1 and L2 first. Okay, so now let me get back. Okay, so let me store this in L2. And it'll be in the, I think, 5th position. We'll have to check. Okay, go to, it should have been the other way around. Hey, wait, let me just check. What is my answer? Oh, my answer is, I've got to put the dimension of it in here. Okay, so let's do 5, and let's store that in the dimension of L2. Okay, sorry, I completely cleared it out. So I needed a dimension there, so I could put something in L5. Okay, so now there it is. In L2 of 5. Okay. So now let me go back to L1. So L1, let me go back to the first one. So my first one goes from 3 to 8. Okay, so let's do 50. Actually, I can go from minus infinity to 8. So I can go from 8 to, the mean is 15.8. Okay. 6. Oh, good. That's good. So that's 6. And I'll put that in L1, in the first one, L2-1. Store. my answer. Store in L2 of 1, the first position. Okay. Good. Next, all the other ones are going to be fine. So the other ones I know are actually, let me go back to this. So 50 distributions. And so now I'm going to go from my second category goes from 8 to 13. So I'm going to go from 8 to 13. Everything else remains the same. 10, and I'm going to store that in L2, the second position. And then I'm going to do 50 norm CDF. I'm going to go from 13 to 18. And I'm going to store that. I know it's going to work in the third position of L2. 14, again, that's bigger than 5. And so I've gone to 18. Now I'm going to go from 18 to 23. So now let me go from 18 to 23. I'm just going to be lazy. And so I'm going from 18 to 23. And I'm going to store that in the fourth position. Okay, so I'm storing that in the fourth position. So that's all of them. And let me do the frequencies. So now, and actually I'll go here, stat, edit. I'll put in my frequencies for L1. So I have 7 for the first one, then 12, then 13, then 9. And then for the last 2, I had a 7 and a 2. I'll combine those to make it a 9. And voila, I'm done. Okay, so, and now let me quit that. And now what I'm going to do is the observed squared divided by expected. So L1 squared divided by L2. L2. And I'm going to store that in L3. So if I look here, so here is, will be my table that I'm going to create. So this is going to be all the values of the expected, all the values of the observed square divided by the expected. I guess I will find that. Let's find the sum, the fifth one, of L1. That should be 50. The sum of L2. That should be 52. The sum of L3. 51.02991963, which means that the test statistic is 1.02991963. So let me go back. So now that I've collected all this, let me go back here. Any questions on the technology so far? And then I'll go back. Okay, so I have here the following. Okay, so I had here all this data. Okay, and so here are these classes. Less than 8, between 3, so less than 8 was 7, 3 and 8 was 12, 13 and 18 was 13, and then 18 to 23 was 9. And then I combined these last two groups together. So if you remember, this was too small. When I looked here, my expected value was just too small. Therefore, I just combined these two groups together. So I made this into a bigger group from 23 and on. So therefore, the observed was now 9, the 7 plus 2. And, well, these were all the numbers I got for my expected. Remember that when I added up the observed, I got 50. When I added up the expected, I got exactly 50 also. And then when I did the observed over, the L1, the squared divided by L2, the observed squared over the expected, I got all these numbers. I add them up. I got the 51.02991963. I subtracted 50 from it. I got the 1.02991963. Okay. And so I have here that my critical value was for the chi-squared with degrees of freedom for alpha being 0.05 was the 9.488. And that my test statistic is not in the rejection region. So I did not reject the null hypothesis. So I didn't reject the null hypothesis. The null hypothesis being that the observed frequency distribution conforms to, fits the normal distribution. The alternative hypothesis being that the observed frequency distribution does not conform to, does not fit the normal distribution, and alpha is 0.05. And so we did not reject the null hypothesis. So yes, we think that it is normal. So yes, there's insufficient evidence to reject the claim that the observed frequency distribution fits a normal distribution with mean 15.8 and standard deviation 6.96. So this is one way of trying to test if some data fits a normal distribution. Any questions about this? Okay, so any questions on section 11.1? Goodness of fit test. Okay, so let's go on to section 11.2, contingency tables. And so a contingency table or two-way frequency table is a table in which frequency corresponds to two variables. So let's say types of procedures. Surgery, weight-bearing cast, non-weight-bearing cast for 6 weeks, not weight-bearing cast for less than 6 weeks. And another variable, success or failure. And so one variable is used to categorize rows. So this was my one variable that was categorizing rows. And second variable is used to categorize columns. So this was my second variable that was used to categorize my columns. Contingency tables have at least 2 rows and 2 columns. You can't be a 1 by 1 or something. So you need at least, 2 rows and 2 columns. The expected, well, the expected frequency. Suppose that we assume independence. So if I'm testing for independence. So if it was independent, well, how would you figure out the probability? Let's see. The probability of success for surgery. Well, you would do what? There 182 successes and 66 surgeries. So the probability of being having a surgery is 66 out of 253. The probability of having a success, given that you had surgery, is, well, again, assuming independence, is 182 out of 253. You wouldn't, because you're not doing conditional probability. So you're assuming that these are independent. So it'd be 182 out of 253. So that's the probability. So probability is 66 over 253 times 182 over 253. So what is the expected frequency? Well, you have to multiply by the total. So one of these cancel. So what is the expected number? Well, the row total times the column total divided by the grand total. Oh, okay. So if I look here, here it is. So the expected frequency is the row total, 66, times the column total, 182, over the grand total, 253. And so the observed was 54. But my expected was, well, the 63 times 182 over 253, the 47.478. And you do that for all of these. So there'll be 8, in this case, 8 observations. And you'll do the expected for each of these using these totals that we've determined here. Okay, so again, basically the terminology is very similar to what we had in the goodness fit test. So test of independence tests the null hypothesis that there is no association between the row variable and the column variable in the contingency table. The test of independent tests the null hypothesis that in a contingency table, the row and column variables are independent. So O is the observed frequency in a cell. E is, well, the expected frequency in a cell. Again, assuming that the row and column vectors are independent. And so that's why you do the row totals and the column total and the row total. R is the number of rows, obviously not including, so in this case, there are 1, 2, 3, 4 rows, not including like the sum here and the labels, etc. C is the number of columns. We assume that the sample data are randomly selected and that they represent frequency counts. If I'm going to be using an asymptotic method, then the observed frequencies have to be at least 5 in each of the cells. If I'm using a chi-squared approximation to the hypergeometric distribution, then my test statistic is the sum of the observed squared over expected minus n, the number of, the sample size. Note, my degrees of freedom, something completely different. So notice uh, before it was always n minus 1. Now it's like almost never n minus 1. So now degrees of freedom are the number of rows minus 1 times the number of columns minus 1. Okay, so let me explain the Yates continuity correction. And so if you can use Yates continuity correction if the expected frequencies are less than 10. And so please note that this correction for continuity may overcorrect. And so this has a problem of overcorrecting. You know, it tries to compensate for it, but it overcompensates. So chi-squared is equal to the sum of the absolute value of the observed minus expected minus a half quantity squared over the expected. So suppose I have a 2x2 contingency table. So let's say this is A, B, C, and D. Then the total for the row is A plus B, C plus D. For the column, A plus C, B plus D, A plus B plus C plus D. So then your chi-squared test statistic is equal to A plus B plus C plus D times AD minus BC squared over A plus B times quantity C plus D times quantity B plus D times quantity A plus C. I always think it's easier just to do it rather than use this formula. Next, Fisher, again, your friend Fisher, exact test. And so this is the test that we're actually performing. It's not in, and so the chi-square test that I showed you from before was the approximation, the approximate test, the asymptotic test that we could use under some criteria. And so we have here that the p-value is, well, let's see. Let's do it using rows, and then we'll do it. So we're going to do the first column. So let's do the first column. So if you do the first column, then the p-value is A plus B, choose A, times C plus D, choose C, divided by A plus B plus C plus D, choose A plus C. Or, let's see, which one do I want to do? Oh, let's do the second. So, or I could do the p-value, and you'll get the same. So I'm going to get, so you only pick one of these because all of them have the same value. So all 4 of these will have the same p-value. Or I could do, pick the second column. So A plus B, choose B, times C plus D, choose D, divided by A plus B plus C plus D, choose B plus D. Or, so I could use either the first column or the second column. The p-value will come out to be the same. Or I could do the first, I could do this way. Yeah, I'll do the first row. So let me do the first row. And so the first row is A plus C, choose A, times B plus D, choose B, divided by A plus B plus C plus D, choose A plus B. Or I could do the second column, second row, or I could do the second row, sorry, the second row. A plus C, choose C, times B plus D, choose D, divided by A plus B plus C plus D, choose C plus D. All four of these give you the same p-value. So you can choose any any column you want to expand on, any row you want to expand on, whichever is easiest for you. So now, one of the criteria, which is a really weird criteria, in order for Fisher to do this test, this hypergeometric test, he had to make the following assumption, that each of these values here, A plus C, B plus D, A plus B, C plus D, A plus B plus C plus D, all of these are fixed the same amount for any contingency table that you draw. And so to actually compute your p-value, you compute your p-value for each of these configurations, and you add them all up where you're going in the same direction of extremity. And this will determine your actual p-value. So where you're keeping all of these, you're fixing your marginals. So this has fixed marginals. So I'm doing this criteria under the assumption of fixed marginals. Okay, so in a second, I'll actually go through that. So this is probably one of the best things since sliced bread. So a 2x3 contingency table. 1 second, let me just grab this off for a second. Okay. So if I have a 2x3 contingency table, let's say I have A1 of one criteria, B1 of another. So if I add these up, I get M1. So A1 plus B1 is M1, A2 plus B2 is M2, A3 plus B3 is M3, AC plus BC is MC, N1 plus N2 is N, A1 plus A2 plus A3 plus A sub C is N1, B1 plus B2 plus B3 plus BC is N2. Then the Brent-Snedeker formula says that chi-squared, the test statistic, is equal to n squared divided by n1 times n2 times a1 squared divided by m1 plus a2 squared divided by m2 plus a3 squared divided by m3 plus a sub c squared divided by mc minus, you're going past this, n sub 1 squared divided by n. And that's the Brent-Snedeker formula. So if you can use this formula, you should use it, because this will save a lot of time. And so now, and you'll see why in a second, why it saves time, what I mean by that. So in the following, the following sample data of random viewers were collected to determine whether the selection of a commercial or public TV channel is independent of the viewer's level of education. Use a level of significance 0.01 to test this. So we have here the education level, postgraduate, graduate, high school, and their selection of TV, commercial or public TV. And so, 150 postgraduates choose public TV, 250 high school students chose commercial TV. Okay, so the sample data randomly selected. The data consists of frequency counts. Well, these here are just observed, but I can certainly imagine that since these are very large, the expected frequencies will all be so large that we can use a chi-squared approximation without continuity correction. So let's do that. So first, and then I'll show you that what the expected are in a minute. So let's look at my hypothesis test. My null hypothesis, the viewer selection of a TV station is independent of the level of education. The alternative hypothesis, viewer selection is dependent on education. Alpha is 0.01. So again, I'm going to assume that I can use my asymptotic method. And so this will be a right-tailed chi-square test. My degrees of freedom are, well, let's see, 1, 2, 3, 1, 2. 2 times 1 is 2. So my degree of freedom is 2. Just taking the number of rows minus 1 times the number of columns minus 1. And so if I look in my table for chi-squared critical values, I get that the critical value is 9.210. Okay, so now let's plug in the data. So I have here 50, 150, 200, 160, 250, 40. Let's add 400, add 350, add 200, add 260, add 290, and so add 750. So now let me show you how to calculate this using the Branch-Schnedeker formula. And so chi-squared is 750 over 400 times 350, all times 50 squared over 200, plus 100 squared over 260, plus 250 squared over 290, minus 400 squared over 750, 213.5308119. Certainly, this test statistic is in the rejection region. So I reject the null hypothesis. So yes, there is insufficient statistical evidence to reject the claim that there's a relationship between viewing commercial or public television and the education level of the viewer. Now, let me show you something for a second. On the TI-84, so let me do this. Oops. And here it is. Okay, so let me do the following. So let me go to matrix. And let's just go to edit. And I'm going to edit the first one. Okay, so let me put in the data. Oh. So this should be a 3x2. Okay, why is it not moving? There it is. Okay. 3x2. 2x3. Sorry, it's a 2x3. 2x3. I can never read. Okay, 2x3. Okay, this is a 2x3 contingency table. So 50, 150, 100, 250, 150, 160, 40. Okay, so that's all my data that I had from before. Let me quit out of this. Let me go to stat. Let me go to chi-square test. Okay, so there, chi-squared is, so I get here my test statistic, 213.5308119, and I also got my degrees of freedom equaling 2. But now, let me show you this. Oops. Let me go to matrix again. Let's go to B. And let me just show you. These are the expected values. So here, all of these numbers here, all my expected values of my, no, darn. Here are all my expected values. There. And so notice that 130, 121 is the smallest. 106, 93. So 93 is the smallest expected value. Those are all huge. Those are all much, much bigger than 5. And so, yes, we could use the asymptotic method because all of those expected values are much bigger than 5. Okay. Let me go back. Okay, so that was all nice and fine because I could use the Branch-Snedeker formula because there were only 2 rows here. So I could use the Branch-Snedeker formula. The following random sample was collected to test whether financial status is independent of drinking habits. And so, drinking habit, heavy drinker, moderate drinker, no non-drinker. Financial status, rich, middle, poor. Use alpha equaling 0.05. Okay. How do you determine rich, middle, and poor? So so how do you consider if someone's rich, middle, or poor? The answer is I'm richer if I'm richer than my neighbor. So the actual thing is you look at the median. And so I think it is the middle. And so you do 20% above and below. And so it is, if you go from anyone below the 30th percentile or 25th percentile, let's say, is considered poor. Anywhere in the middle, 50% is middle, and anyone in the upper 25% is rich. That's usually like, the criteria, it could be plus or minus 5%, but that's usually the criteria that people usually give. Then there's the super rich, the ultra rich, and the ultra rich, which are, so I think the super rich is 95th percentile. The ultra rich is the 1 percentile. Ultra rich is the the thousandth of a percentile. Okay. So again, the sample data randomly selected. Data consists of frequency counts. The expected frequencies are large. That observed is small, but it's still not that small. So we can do this without continuity correction. And we'll explain why in a few minutes. Hypothesis test, null hypothesis, that these are independent variables. Alternative hypothesis, these are dependent variables. Alpha is 0.05. So null hypothesis, there's no relationship between financial status and drinking habits. Alternative hypothesis, there is some relationship between financial status and drinking habits. Alpha is 0.05. This will be a right-tailed chi-square test, we're assuming. So my degrees of freedom is 4. Alpha is 0.05. So my critical value for chi-squared is 9.488. Okay, so we have here 3 columns, well, 3 rows. So 3 minus 1 is 2. We have 3 columns. 3 minus 1 is 2, times 2 is 4. So that's why degrees of freedom is 4. And so let's add up 120, 150, 70, 125, 140, 70, 340. Okay, so let's now do this. So this is going to be a pain. Okay, so we have here, well, I have to do it this way. Yeah. So I have here 40, 60, 20, 50, 55, 45, 35, 25, 10. Okay, so let's do this. And so let's do the 40. 125 times 120 divided by 340. Which I think is, yeah, it's this one. So 125 times 120 divided by 340. There it is. Okay. That's just for one calculation. So now let's do the next one. And so the next one, and then you'd have to do 40 squared divided by this 44 to get the 36.266. Okay, so now let's do the next one. So 140 times 120 divided by 340. 60 squared divided by this number. And then for this guy, 75 times 120 divided by 340. Take the 20 squared divided by this number to get the 15.11. Next, this guy here. 125 times 150 divided by 340. 50 squared divided by this number is the 45.33. Next, 140 times 150 divided by 340. The 55 squared divided by this number gives me this number. 45. So 75 times 150 divided by 340. The 45 squared divided by this number gives me the 61.2. This number, 125 times 70 divided by 340. 35 squared divided by this number is 47.6. 140 times 70 divided by 340. The 25 squared divided by this number gives me this number. And lastly, 75 times 70 divided by 340. And then 10 squared divided by this number gives you this number. So as you can see there's some, why isn't it changing orientation? Change orientation for me. Okay, here, wait. Okay, let's go to this guy then, and then it'll change orientation. Yeah. Oh, California terms. What education vote? I don't know what this was related to.
In terms of the, I was thinking more of like cost of living and how people are just not making it financially. That's all.
Oh. In California terms, what is rich? What makes you rich?
I don't know. Yeah.
So the last one I saw, that saw
something vital to the security of the encryption.
right. Okay, so last one I saw, meaning like a week ago. So about a week ago, I was reading an article in newspaper. So their definition of rich was the 80th, which is I think the 8th percentile, was I think $175,000. Let me stop this for a second.
Target location scans are complete.
It was $175,000. So their criteria of which I thought was really, really small was 170 in California. People making 175,000 or more. There was another article I read, which was $200,000 or more, which gives you in the 90th percentile. So 90th percentile for families was 190. It was 190,000 or more in California. Again, which I didn't think was that high. So that's what they consider rich. All I can tell you is that's not really rich. So, or at least I don't consider that rich. Okay, so you would then add up all these, and then subtract. So you get 15.50430839. The test statistic is in the rejection region, so you reject your null hypothesis. So no, there's insufficient evidence to support the claim that financial success is independent of drinking habits. So if you notice here, it's a lot of calculations. So this is a lot of work, a lot of calculations here. And, this was much easier. So this made your life really easy. If you can't use the branch genetic order, you've actually got to go through all this, which is much longer. Again, let me show you how to do this on your calculator. So I wonder if I can do it. Let me see if I can do it on this other calculator, my cheap calculator, my free calculator. Let's see if they have matrices. Oh, they do have matrices. Okay. Edit. Okay, let's edit this. And I want a 2x3. Yeah, okay, so. Oh, no, this is a 3x3. This is a 3x3. And so let's put in, here, 40, 50, 35. Oh, I bet you I did this before. 20, so 20, 45, 10. Okay, so there are all the good. There are all the numbers there. Okay, and then I'm going to exit out of this. And so now let me go to stat test chi-square test. No, that's not the correct test. Stat test. There must be a goodness of fit test. Here's a chi-square goodness of fit test. So let's do a chi-square goodness of fit test. Degree of freedom is 2 times 2 is 4. Okay, so 4. So my degree of freedom, strange you had to tell what the degree of freedom is. So my degree of freedom is 4. And so, yes, 4. So let's calculate this. Okay, so enter a matrix. So instead of, so I did that. Okay, so now let me quit this. What the world? Enter a matrix instead of a list. What are they talking about? Okay, so now let me look. Matrix B. Oh, okay, good. So there are all the numbers. So here it is, the 44, 49, 26, 55, 61, 33, the 25, 28 in there. Okay, so that's all those. Okay, so, but then what you'd have to do is to figure out this guy. So to add up all these, it's not going to be easy. So you'd have to do the entries. Okay, so none of that is easy. Yeah. So you could figure out B. Oh, God. Problem with having this free stuff here. I guess there's no way we'll get rid of that till it stops it. Okay. So you could actually, you have to put a parentheses, I guess. So 1, 1. Okay, that would give you the 44. Oh, they don't like that. They don't like that criteria here. It's the first entry. Unless they want that. Let's just see. B. The first entry, maybe they want 1, 1. Yeah, it doesn't do. Oh, yeah, they don't want that. Okay, so forget this. Okay, they're not doing the same thing. Sorry, they're not doing the same emulation as the TI-84. Okay, so so that at least gives you all these numbers here, but you still have to do. So it gives you all these numbers, but you still have to then, do all these individually, and then add up all these stuff. There is a way usually to enter it in, to flatten it out, but again, flattening it out is just as hard almost as doing it by hand. Okay, so notice that without the branch genetic core, it's a lot of work. So okay, so now let's see how much work it really is. Okay, so let's do the following. And I'm going to do actually the same criteria, the same problem over and over again, so that you can understand the real process that we're doing. Okay, so the following data show the number of boys who failed the vision test and who did and who did not wear glasses. The group was classified into two categories, namely passed and failed. So they passed or they failed their vision test. They either wore glasses or they did not wear glasses. Okay, so, and here are the numbers. Use Fisher's exact test to test whether there's a relationship between those boys who passed the vision exam and whether they wore glasses. So, sample data randomly selected, yes. And the data consists of frequency counts. Okay, so now that's it. I don't have to worry about if they're large or small numbers here. So, null hypothesis. The variables are independent. There's no relationship between passing your vision test and wearing glasses. Alternative hypothesis. It's dependent. There is a relationship between passing the vision test and wearing glasses. Let alpha equaling 0.05. So the test of independence is a hypergeometric test. So our chi-squared test that we've been using is an approximation to the hypergeometric distribution. And so that's why we needed the assumption about the fact that each frequency distribution must be greater than 5 to use this chi-squared approximation. So let me show you all the possible configurations of our contingency table where we use the criteria of fixed marginals. So here's my table. 10, 15, 1, 13. Okay, so now 10 plus 15 is 25. And so let's suppose that this goes from 10 to 9. If this goes from 10 to 9, since this sum is 25, then this number must be 16. 10 plus 1 is 11. So if this was 9, then this must be 2, so that they add up to 11. 15 plus, well, let's just say 1 plus 13 is 14. So if this is 2, this must be 12. Okay, so good. So now notice the following. I subtracted 1 here. So 10 went to 9, which caused the 13 to also go down to 12. So if I subtract here, I also subtract here. And if I subtract here, then I must add here. So subtract along this one causes me to add along this one. Okay, so let's keep going. So notice if I subtract 1 here, so if I add 1 here, so I have to add, so that becomes 10 becomes 11, 13 becomes 14, then I've got to subtract. 15 becomes 14, 1 becomes 0. I can't go any further. Okay, so now, and so notice I'm keeping the marginals fixed. That this is, if you add this way, you get 25, add this way, you get 14, add this way, 11, add this way, 28. And that occurs for all of these possible contingency tables. So let's keep going. So let's keep subtracting 1. So that becomes 8, 11. Add 1, 17, 3. Subtract. So 7, 10. Add 18, 4. Subtract 6, 9. Add 19, 5. Subtract 5, 8, 26, 4, 7, 21, 7, 3, 6, 22, 8, 2, 5, 23, 9, 1, 4, 24, 10, 0, 3, 25, 11. I can't go any further. I can't have negative numbers here. So can't go any further here, can't go any further here. So these are all possible contingency tables. Now, I want contingency tables that are just as extreme as the given data. Here's my given data. Well, what side is it? Is it more to this side or to this side? Well, obviously, this guy is closer to this one. So the only tables that I include are these two tables. These are the only tables just as extreme as my sample table, my sample data table. Okay, so if it was like this guy here was my sample data, then I'd have to include all of those. Okay, so good. So now let's determine my p-value and add them up for each table. So again, sum across is 25, 14, down 11, 28, and 39. So again, 25, 14, 11, 28, 39. And so let's see, I don't care. I'll go along the first column. So I'll do the first column. So if I do the first column, I get 25, choose 11, times 14, choose 0, divided by 39, choose 11. And let's do 25, choose 10, times 14, choose 1, over 39, choose 11. And I get 0.029999632224. If I did the second row, note I get the same thing. And so, row, I'm gonna do the second row. Sorry, I'm gonna do the row. And so I'll do 11, choose 0, times 28, choose 14, divided by 39, choose 14. 11, choose 1, times 28, choose 13, divided by 39, choose 14. And you get the same amount. Again, it doesn't matter. And you know, and I could have chosen, to mix them up. So it really doesn't matter. So long as in one calculation, it's all the same. Okay, so this is less than 0.05. So that means that we are in the rejection region. So I reject the null hypothesis. So yes, there's insufficient evidence to reject the claim that there's no relationship between wearing glasses and passing the vision test. So so note that in order to use Fisher's exact test, we need to assume that each time we conduct this experiment, we have the same number of boys that passed the vision test, the same number that failed the vision test, the same number that wore glasses, the same number that did not wear glasses. And so this is called testing under the assumption of fixed marginals. So the chi-square test does not need to make this assumption about fixed marginals. And so that's sort of good. So that's one of the good things about the chi-square test, that you don't need to assume fixed marginals. Okay, so this is my p-value. And I think, so now let's redo this. So any questions so far? So this is the test that I should have been doing. No, it is not. No, it's not. Yeah, no, not a lot of money. Okay, so now the following data show the number of boys who failed a vision test and who did or did not wear glasses. The group was classified into two categories: passed or failed. Same as before. Use a chi-square test without continuity correction to test whether the relationship between boys who passed the vision exam and whether they wore glasses. So the sample data is randomly selected. The data consists of frequency counts. However, since we're approximating discrete distribution by continuous distribution, we should use continuity correction, but the instructions tell us not to. Also, the requirement that the expected frequencies should be at least 5 is not satisfied. But again, we're told to, so we do as instructed. Because we want to show you, we want to compare. So we want to compare things. So my hypothesis test is, well, that these variables are independent. There's no relationship between passing the vision test and wearing glasses. Alternative hypothesis, that these are dependent. There is a relationship between passing the vision test and wearing glasses. Alpha is 0.05. My degrees of freedom, number of rows, 2 minus 1, times number of column, 2 minus 1, is 1. I can use the branch static core formula. And so it's just 39 squared divided by 25 times 14 plus times 10 squared divided by 11 plus 15 squared divided by 28 minus 25 squared divided by 39, 4.78 455 4731. And so let's compute my p-value, which is, well, since it's a right tail test, I'll have to, the chi-squared CDF gives me left tail. So I'll have to do its complement. So 1 minus chi-squared, I started 0, and then that my 4.78 455 4731. With degree of freedom 1, I get 0.0287160709, which is less than 0.05. Therefore, I reject the null hypothesis. So yes, there's insufficient statistical evidence to reject the claim that there's no relationship between wearing glasses and passing the vision test. Okay, good. By the way, the reason I'm figuring out p-values, because I want to do a comparison. So I want to do, again, I'm trying to do a comparison. Okay, so the p-value is too small. So I got a too small p-value there. But at least it had the same conclusion. Next, let's do the following. The following data show the number of boys who failed the vision test and who did or do not wear glasses. The group is classified in 2 categories, pass, failed, same as before. Use the chi-square test with Yates continuity correction, test whether the relationship between boys who passed the vision exam and whether they wore glasses. So again, sample data randomly selected, done this 50 times, or well, 3 times. Data consists of frequency counts. Again, we're approximating discrete distribution by continuous distribution, so we should use continuity correction. The assumption for this asymptotic approximation, the expected values are greater than equal 5, is not satisfied. So again, we shouldn't be using this, but they tell us to, so we will. So again, same hypothesis test. Null hypothesis, that these variables are independent. There's no relationship between passing a vision test and wearing glasses. The alternative hypothesis, that these are dependent. There is a relationship between passing a vision test and wearing glasses, and alpha is 0.05. This will be a right-tailed chi-squared test using continuity correction. So my degrees of freedom are, well, 2 minus 1 times 2 minus 1. So 1 times 1 is 1. And so I have here my table, my contingency table. So let's invoke Yates continuity correction. I'm going to do it 2 different ways. Well, the second way is the one I prefer because I think it's much easier. And so my observed are 10. My expected is, well, let's see, 25 times 11 divided by 39. Again, for 15, 25 times 28 divided by 39. For 1, 14 times 11 divided by 39. For 13, 14 times 28 divided by 39. And so we have to do absolute value of observed minus expected minus 0.5 squared minus half squared over expected. So for this one, it's 10, the absolute value of 10 minus, well, the 275 over 39 minus a half squared over the 275 divided by 39, 0.85, 0.3729604. Again, you have to do absolute value 15 minus 700 over 39 minus a half quantity squared over 700 divided by 39, and then calculate the number. Absolute value of 1 minus 154 over 39. Take that absolute value, subtract a half squared, divide by 159 over 154 over 39. And then lastly, absolute value of 13 minus 392 over 39, and absolute value minus a half squared over the 329 over 39, and add up all those numbers to get 3.299533859. Okay, and that is your test statistic using the continuity correction, the Yates continuity correction. Now, I like this other method. So it seems like a lot of horrible numbers in a calculator. So this is what I like to do. So recall my original, hopefully it'll switch back. And so my marginals were 25, 14, 11, 28, 39. Okay, good. I subtract a half from each of these. I have to add a half to each. Remember, I want to add a half. I should start out this way. I want to add a half this way. So I have to add a half this way. So 1.5, 15.5, I have to subtract a half from each of these. 9.5, 11, 12.5 to get my fixed marginals. Okay, good. But now I can do, so now with this, I can do the branch phonetic core. And so using branch phonetic core, I'll just do 39 squared divided by 25 times 14 times the quantity 9.5 squared over 11 plus 15.5 squared over 28 minus 25 squared over 39. Now look, same number, 3.299533859. I think this is much easier and more understandable what you're doing rather than this formula. So I think that formula is much worse than just doing this, balancing things off. Okay, so now my p-value again is 1 minus chi-squared from 0 to 3.299533859. Degree of freedom again is 1. So I got 0.0692995457, which is greater than 0.05. So therefore, I'm not in the rejection region, so I do not reject the null hypothesis. So no, there's insufficient evidence to support the claim that there's no relationship between wearing glasses and passing the vision test. But now, note the following. We had yes when using the exact method. You know, we rejected, or maybe I should say that, with the exact method, we rejected null hypothesis. Without continuity correction, we rejected null hypothesis. With continuity correction, we did not reject the null hypothesis. So we're actually getting the wrong result. So with continuity correction, we actually got the wrong result. So note, for Fisher's exact method, we got a p-value of 0.0299632224. So this is the value we should get for p-value. For chi-squared method without continuity correction, we got a p-value of 0.0287, so it's too small. 160790709. So then we'd use the chi-squared method with the 8 continuity correction, and we got a p-value of, look at this. So this was, this was too small. But this 0.0692995457 is much too big. So, we were off by 1/1000th. We're off by 1/1000th. And so we invoke continuity correction. And now we're off, by 400th. So it's much worse. So, we try, it was too small. Then we got something that was much, much too big. And so it is completely overcompensated. So note that continuity correction actually led to the wrong conclusion. So thus, even though you should use continuity correction, it is actually best not to use continuity correction for the chi-square test method for contingency tables. So even though I know we're supposed to use continuity correction, I never actually use continuity correction in this case because it's really bad. It completely overcompensates. In other words, this was 29 or 299, whereas this was 287, a little bit too small. But we got 693, which is gigantically just completely off. So if you can use branch genetic core, always use branch genetic core. But if you can use the asymptotic method, you should use the asymptotic method. One, it's much faster. Notice dealing with all those hypergeometric distributions was a pain, doing all that calculation. And it's not that far off. So long as the criteria. Notice the reason that this was, even though the expected value was too small, it was less than 5, it still didn't give us a horrible amount. So, if we actually satisfied all the conditions for the asymptotic method, it actually, gives us a pretty good estimate. It also works in more cases. It works without these fixed marginals. And so that has a definite advantage. So if you can use this asymptotic method, use it. It is a fairly powerful method to use. Okay, so in experimental immunization of children with chickenpox, the following results were recorded if the test of immunization from chickenpox is independent of whether one gets disease. And so, if they have affected with disease, unaffected, inoculated with the, with your vaccine, or not inoculated. Okay, so sample data randomly selected. Data consistent frequency counts. We use the chi-squared approximation without continuity correction. We can certainly assume, certainly it seems like the expected value will be greater than 5. Null hypothesis, varies of independent. Being immunized does not affect whether you get chickenpox. Immunization is not affected. Alternative hypothesis, variables are dependent. Being immunized affects whether you get chickenpox. Immunization is effective. Let alpha equal 0.05. This is a chi-squared right tail test without continuity correction. Degrees of freedom are, 2 minus 1 times 2 minus 1. 1 times 1 is 1. And so alpha is 0.05, degrees of freedom is 1. So the critical value for chi-squared is 3.841. And so I get here, let's add 65, 50, 115, 55, 60. And so use branch Snedeker. So chi-squared is equal to 115 squared times 65 divided by 65 times 50 times the quantity 25 squared over 55 plus 40 squared over 60 minus 65 squared over 115, 5.254079254. My test statistic is in the rejection region, therefore I reject the null hypothesis. And so if you want to find the p-value, 1 minus chi-squared CDF going from 0 to 5.254079254, degrees of freedom 1, 0.021895,383. So reject the null hypothesis. No, there's insufficient evidence to support the claim that immunization is independent of getting chickenpox. There's insufficient evidence to conclude that immunization is ineffective. Okay, so next, does it appear that the choice of treatment affects the success of treatment for foot procedures? Use a 0.05 level of significance to test the claim that success is independent of treatment group. Okay, so success, failure, and the differing types of treatments. So based on the study, we treat the subjects as being randomly selected and randomly assigned to different treatment groups. The results are expressed as frequency counts. The expected frequencies, hopefully, are all over 5. Gotta check that, but null hypothesis. Success is independent of treatment. Alternative hypothesis. Success and treatment are dependent. Alpha is 0.05. So we'll use a chi-squared test, right tail chi-squared test. And we're going to do this without continuity correction. And so I have here, well, the critical value is 7.851. And if I add these up, I can use the branch Snedeker formula. I'll use the branch Snedeker formula. 66. $92, 73, 22. Okay, 253. Okay, so then chi-squared is equal to 253 squared over, oh, I didn't add up these. Okay. Then that's going to be 70 or something. Okay, so it's 3, 5, 11, 71, yeah. Okay, so 182 times 71. 55, 54 squared over 66. 41 squared over 92. 70 squared over 73. 17 squared over 22. 182 squared over 253. Okay, so let's do that on my calculator. Let's do it here. $253 squared. Hmm. 41 squared over 92. 70 squared. 17 squared. 182 squared over 253. So I get here 58.393265.0169. So again, the branch-netted core formula, really nice. And so our test statistic is in the rejection region. So I reject the null hypothesis. Okay. And so it appears that success is independent of treatment. So although the test does not tell us what treatment is best, we see success rates of 81%, 44%, 95%, 77%. So we suggest, it seems that the best treatment is the 95% one, non-weight bearing cast for 6 weeks. Okay. Test of homogeneity. In a test of homogeneity, we test the claim that different populations have the same proportion of success of some characteristic. So for all tests of homogeneity, well, they're success and failure. Number of successes, number of failures. So it's always a 2x C contingency table. Therefore, I can always use the branch-netted core formula. So in a test of homogeneity, we test the claim that different populations have the same proportion of success for some characteristic. So how do we distinguish between a test of homogeneity and a test of independence? In a typical test of independence, the sample subjects are randomly selected from one population and the values of two different variables are observed. In a test of homogeneity, subjects selected from differing populations separately. And usually it's several different populations. And so, let's do the following example. In the departmental statistics examination, 125 daytime students passed, 57 of 75 evening students passed, 36 of 50 off-campus students passed. Test whether daytime students, evening students, and off-campus students passed in the same proportion. Okay, so let's do that. Null hypothesis: the proportion of daytime students who passed is equal to the proportion of evening students who passed is equal to the proportion of off-campus students that passed this particular statistics examination. The alternative hypothesis: the proportions are not all the same. So, there's, I don't know which one is different, but at least one of them is different. Let alpha equal, since they didn't tell us alpha, 0.05. So there are 1, 2, 3 categories. So the degree of freedom is 2. This will be again a right-tailed chi-square test. I'm assuming that we can do this asymptotic approximation. Certainly all the numbers are huge. So degree of freedom is 2. Alpha is 0.05. So the critical value for chi-squared is 5.991. Let's add, and so all these numbers are given. Let's add up these numbers. And so I get 193, add up these numbers, I get 250. 250 minus 193 is 57. And now these are the only numbers I need to plug into the Branch-Snedeker formula. So I don't need all these other numbers. I could calculate them, but they're unused. So I'm not going to do it because I'm lazy. So chi-squared is 250 squared divided by 193 times 57 times the quantity. 100 squared divided by 125 plus 57 squared divided by 75 plus 36 squared divided by 50 minus 193 squared divided by 250. And so I get 1.386237615. My test statistic is not in the rejection region, so I do not reject the null hypothesis. So yes, there's insufficient statistical evidence to reject the claim that daytime, evening, and off-campus students passed in the same proportion. In a random sample in East Jerusalem in 1967, 6 of 120 Christian, 3 of 50 Armenian, 17 of 120 Jewish households, and 10 of 215 Muslim households had a TV set. Test whether the proportion of having a TV set are all the same. And so, null hypothesis, proportion of Christian is equal to the proportion of Armenian is equal to the proportion of Jews is equal to the proportion of Muslims that have a TV set. Alternative hypothesis, proportions are in East Jerusalem. The alternative hypothesis, the proportions are not all the same. Alpha is 0.05. Degree of freedom is, well, there's 4 categories. 4 minus 1 is 3. And so this is going to be a right-tailed chi-square test. And so I have that, well, again, looking in my table for chi-square, given degree of freedom is 3, and my right tail is 0.05, I get 7.815. I can use Branch-Snedeker, so let's use Branch-Snedeker. So add up all these, 36, add up all these, 605 minus 36, 569. And so chi-square is equal to 605 squared divided by 36 times 569 times the quantity, 6 squared over 120 plus 3 squared over 50 plus 17 squared over 220 plus 10 squared over 215 minus 36 squared over 605. 2.083574304. My test statistic is not in the rejection region, so I do not reject the null hypothesis. So yes, there's insufficient statistical evidence to reject the claim that the proportion of Christian, Armenian, Jewish, and Muslim households that have a TV set are all in the same proportion. Any questions about that? Okay. This might be the last one. A survey taken by health officials indicate that in Maryland, 28 of 122 oil users use olive oil. That means that almost no one uses olive oil. Does anyone not use olive oil? Does any student here not use olive oil? I use olive oil for everything. Okay. I guess everyone else occasionally uses olive oil also. Okay, so in Maryland, 28 of 122 olive oils use olive oil. In Virginia, 15 of 85 olive oil users use olive oil. In Delaware, 9 of 56 oil users use olive oil. In New York, 42 of 220 oil users use olive oil. Test whether the proportion of oil users using olive oil are the same. So, null hypothesis. Proportion in Maryland is the same as the proportion in Virginia, is the same as the proportion in Delaware. New York, we went all the way to New York, is equal proportion in New York. These were all around Washington, D.C., then this one further up the East Coast. Okay, so all the proportion of these of oil users that use olive oil are all the same. Alternative hypothesis: the proportions are not all the same. Alpha is equal to 0.05 because they don't tell us. The degree of freedom is, well, there's 1, 2, 3, 4, and so 4 minus 1 is 3. So mid degree of freedom is 3, alpha is 0.05. Therefore, my critical value is 7.815. So again, you add up all these, 94, add up all these, 483, minus 94 is 389, which is good, that they just gave us 28 out of 122, 15 out of 85, 9 out of 56, 42 out of 220, because really this is all we need to know. So that in order to use branch standard core. So let's use branch standard core. And so chi-squared is equal to 483 squared divided by 94 times 389 times the quantity 28 squared divided by 122 plus 15 squared divided by 85 plus 9 squared divided by 56 plus 42 squared divided by 220 minus 94 squared divided by 483, 1.556086386. My test statistic is not in the rejection region, so I do not reject the null hypothesis. So yes, there is insufficient evidence to reject the claim that the proportion of oil users that use olive oil are in the same proportion in Maryland, Virginia, Delaware, and New York. Okay. Oh, can't do that.